the last piece of material which was on the second exam, RC circuits. And after that, we moved into the world of magnetism, right? So pretty much that's what we discussed after that. So when we moved into the world of magnetism, of course, we introduced some conventions, some simple idea, because it was completely new world for us. And then the first fundamental law which we introduced is Biot-Savart law, which allows us to find magnetic field produced by a wire with a current. So if you have a wire of any shape with current I, then of course we write down the law in a differential form, because different parts of the wire are going to be in different conditions, right? So we took infinitesimally small section ds. Let's say we want to find magnetic field at that point. R hat, it's a direction to that point. And Biot-Savart law, mu naught over 4 pi, mu naught was our new constant, and then I ds cross r hat divided by r squared. What we need to remember, direction of ds. Direction of ds is determined by the direction of the current. Basically, you need to remember that. And of course, this formula will be on the formula sheet. Although usually application of this is a little bit more complicated than the rest of the formulas. Then, if you apply this formula for an infinitely long straight wire, we can get expression for the magnetic field created by infinitely long straight wire. So, actually I should have added, so that what is r small over here, if we're interested in the magnetic field at this point, that's r, perpendicular distance from the wire to the point in question. I forgot to show you. Then, magnetic field lines, we remember, they form circles. How can we find direction of those circles? We need to apply right-hand rule number 2. Outstretch your thumb in the direction of the current and curl your fingers around the wire, so that will be direction of the magnetic field lines. Great, so after that, we found there is an alternative way of finding magnetic field using Ampere's law, which is one of the Maxwell's equations, right? So integral over the closed loop B dot ds equals to, again, our new constant times enclosed current, right? So we will discuss it a little bit. We're not going to solve any problem about this law today, because not much of a variety of problems which can be solved, and those problems which you can review from our notes of the lecture or recitation class, because I can offer only, I don't know, find magnetic field created by a solid cylindrical wire or cylindrical wire with a hole, and we discussed that all, right? So you just need to review it. Great, so this and that can be used to find magnetic field, but it's not enough in order to have a foundation. So you also need to introduce magnetic force. So we introduced two formulas. This is fundamental formula, that is kind of practical. So fundamental, if you have a charged particle which moves with velocity v, and if it is exposed to the magnetic field, then of course it is going to experience magnetic force. It's just a fact which we observed. And this formula happens to work, it happens to explain the interactions between the magnetic field and the charge. F equals Q, V cross B. If you want to find direction of the magnetic force, there are like 2 steps, okay, 1.5 steps. First, you need to take a cross product, find the direction of the cross product, and then you need to quickly check the sign of the charge. If the charge is positive, this direction is going to be the direction of the force. If charge is negative, that then found direction you have to flip in order to find the actual direction of the force. Then this formula can be used. From this formula we can derive this formula. So if you have a straight piece of wire with a current, and that current, okay, that wire is exposed with to uniform magnetic field B, right, of some length L, so that length L of the wire is exposed to the magnetic field. So then we can find the sort of net force acting on this piece of wire by using, right, I, L cross B, again cross product, so we need to use right-hand rule in order to find direction of the force, right? Great, so after that we moved into Faraday's law. We found that Faraday introduced some interesting phenomena, right, blah, blah. So if you have any loop exposed to the magnetic field, and if that magnetic field, if there is a loop exposed to the magnetic field, of course there will be flux. If that flux changes in time, if that flux changes in time, then somehow mysteriously EMF will be produced in the loop, right? So that's how we can find that EMF produced in the loop minus a rate of change of the magnetic flux. Magnetic flux, number of magnetic field lines crossing a certain surface, right? This is correct for the simplest possible situation, uniform field, flat surface, and that's what most of the time we use. Then that minus allows us to find direction of the induced current and direction of EMF. Instead of dealing with that minus, we introduce Lenz's rule because it's more convenient to use Lenz's rule. So, and the Lenz's rule works like this. So, physical philosophical idea. Any loop any loop doesn't like changes in the magnetic flux, right? So if magnetic flux is constant through the loop, then loop doesn't do anything. So EMF will be zero, current is not going to be produced, nothing will happen. But if flux, for example, start increasing flux through the loop, then of course that loop doesn't like it, and of course it starts repelling, right? So at least I compare it to that phenomenon. So basically it will start, it will produce EMF and start driving current in such a direction so that induced magnetic field, which is produced by that current, will be in the opposite direction within the loop to the direction of the external magnetic field. Okay, we will practice that. Right, and then once you know the direction of the induced magnetic field within the loop, you can apply right-hand rule in order to find direction of the induced current which produced that magnetic field. Then, second situation, if magnetic flux is actually going down in time, then in this case, loop becomes supportive and it tries to support dying flux. So in that case, it drives induced current in such a direction so that the induced magnetic field is in the same direction as the external magnetic field, right? And then, of course, once you know this direction, you can use you can find the induced current. Okay, so then after this, we introduce inductance. We introduce inductance as the ratio of the total magnetic flux to the current, right? And typical inductor, solenoid, right? So if you apply this formula to find inductance of a solenoid, we found this formula, mu naught n squared, where n number of loops, L length of the inductor, and A is the cross-sectional area. Right, then we also found interesting phenomena. If something happens to the current, then it's possible to produce potential difference across an inductor. Right? Although inductor is just a piece of wire, but under certain conditions, it's possible to produce potential difference across an inductor. So delta V. So if this is inductor, so current flows in, here current is out, so this is initial point, this is final point. So delta V, it's a V final potential, electric potential at this point minus electric potential at that point, right? And it is equal minus L. L is inductance of the solenoid, inductance of an inductor, right? And times rate of change of this current, basically how fast this current changes through the solenoid, right? Again, we will practice this. Great, so after this, we started slowly moving into optics. And as a first step, we refreshed, for some of you, for some of you it's new, we introduced traveling wave equation, right? Which describes any traveling waves. Longitudinal, transverse, it doesn't matter, right? So, for example, in the case of a chord, I forgot to take my chord, right? So, in the case of a wave on a chord, y, it's a displacement of particles chord horizontal, wave propagates in this direction, and particles moves up and down, up and down. So y defines position of those particles as they move up and down. Then, but wave propagates in the x direction. So it's an amplitude periodic function, and then inside the periodic function we have a phase of the wave, which consists of kx plus minus omega t plus phi naught. K, wave number, we define it in this way. It's basically spatial frequency. 2 pi divided by spatial periodicity. Then omega, angular frequency, basically temporal frequency, and it is introduced as 2 pi divided by temporal periodicity. Right. So here 2 pi divided by spatial periodicity, here 2 pi divided by temporal periodicity. Then plus minus, plus means that wave propagates in the minus x direction, minus indicates that wave propagates in the positive x direction, right? Then there are two ways of finding speed of this wave. It's either omega versus k, or lambda wavelength times frequency. It depends what is given in your case, what you know about the wave in that case, in that particular problem. Okay, great. So then after this, we moved into electromagnetic waves. And so in the electromagnetic wave actually consists of two parts. Electromagnetic wave consists of two parts. Electric field traveling wave, transverse, and magnetic field traveling wave, also transverse wave. And together they form electromagnetic wave. In this case, electromagnetic wave propagates in the x direction, right? So all the time in the electromagnetic wave, these three directions, magnetic field, electric field, magnetic field, and direction of wave propagation, they must be perpendicular to each other all the time, period. Then also in the electromagnetic wave, amplitude of the electric field and amplitude of the magnetic field, they are connected through the speed of light. Electric field amplitude is way, way, way larger than the magnetic field amplitude. Right, so here I sketched, and pretty much electric field and magnetic field, they oscillate in unison. All the time they share ups and downs, they reach zero at the same time, at the same moment, right? So complete unison. And so here's the mathematical expression for the electric field. It's basically electric field traveling wave equation, right? So E sub y, this subscript tells us that the electric field oscillates in the y direction, but wave propagates in the x direction, right? So then amplitude, again, periodic function sinus here, again, wave number, x. In this case, wave propagates in the positive x direction, again, angular frequency, initial phase, and then magnetic field. Again, subscript indicates that magnetic field oscillates in z direction, right? But the wave propagates, again, in the positive x direction, of course, is for the electric field, right? And so, as I said, electric field and magnetic field, they oscillate in unison. It means that this part, sine kx minus omega t plus phi naught, sine kx minus omega t plus phi naught, exactly the same for the electric field and magnetic field. So if you know this expression, you can write this part for the magnetic field immediately, because that structure under the sine function is exactly the same. Great, so then after that, we looked at the interference of any wave. And we use, for example, acoustic waves, I think. Oh yeah, of course, electromagnetic waves also used, but here I used acoustic situation. So let's assume that we have two speakers, 1 and 2, right? So they create two-dimensional waves. And these are basically, I drew wave fronts. You remember wave front, collection of crests, right? And so, of course, we assume that this wave produced by this speaker and wave produced by that speaker are identical, the same amplitude, the same wavelengths, the same frequency. In that case, they interfere. And if we take, for example, this point, and we can ask ourselves, so what can we see at this point, constructive or destructive interference? In order to answer this question, we need to construct this. We need to look at this condition. 2 pi over lambda times delta r. Delta r, it's a path length difference. It's basically r2 minus r1. It's just additional distance that second wave must to cover in order to reach the point in question relative to the first wave. Then delta phi naught, inherent phase difference. That's where students most of the time has big troubles, right? So inherent phase difference most of the time is given in the statement of the problem. If problem says two antennas out of phase antennas, it means that inherent phase difference is pi. If it says, I know, two speakers in phase, it means delta phi naught is 0. And so if you calculate this, and you will end up with m times 2 pi, where m is an integer. Okay, I forgot to write that down. M equals 0, 1, 2, 3, and so on in integer. So if you have integer number of 2 pi's, it's constructive interference at that point. If you can calculate this, and you will end up with integer plus 1, 2 times 2 pi, then it's a destructive interference. Again, we will look at one example. And the final piece this week, which we discussed, double-slit and diffraction grating. For double-slit, you have two slits at a small distance d, 0.5, 0.2, 0.3 millimeters, right? And if you position screen at some distance L, and of course you need to eliminate those slits with the monochromatic source, laser for example. Right? And over here on the screen you're going to see interference fringes, collection of bright and dark spots, right? Equally spaced. And so position of those bright spots we can find using this formula Ym. It's a distance from the center of the screen to the point where this or that bright spot is. Right? For example, Y2, it's this distance from here to there, right? And can be found M, again integer, lambda L divided by D. D is the distance from the slit to the screen. Then natural transition from double slit to diffraction grating, right? In an attempt to improve the work of that system if you try to use it, for example, as a spectrometer. So we increase number of slits from 2 to several thousands. And distance between slits we reduced by a factor of 100. As a result, you end up with diffraction grating. And now interference pattern is much better, much better to use in the lab, for example, as I said, if you try to use it as a spectrometer. So at the center, bright spot corresponding to integer m equals 0, then bright spot at some distance corresponding to m equals 1, m equals 1, m equals 2, 2, 3, 3. Okay, so positions of those bright spots can be found. Angles can be found using this formula. It's basically the same as we derived for that. D, distance between slits, times sine of the angle to this or that bright spot equals to integer number of wavelength. And since it's not practical to deal with these angles, it's better to switch to, again, like here, to the distances from the center of the screen to the position of this or that bright spot. Ym equals L times tangent of this angle, which you found in the previous formula. So pretty much this is the scope. So at least 60 or 70% of the exam will be based on this material. Right? So, and then the rest will be, of course, based on the previous materials from the previous exams. Okay, enough of this quick review. So now problems. Let's start with, for example, this. Because application of Biot-Savart law, we solved only one problem, and we spent like, I don't know, 35 or 40 minutes solving only one problem. So it's not that trivial to use that formula. So, problem number 1. So we have two parallel wires. Okay, the first one. Let me draw it over here. So the current flows into the board, I1. Okay, I will write down the values in a second. Then there is a second current. Okay, let me position it here. I2 flows out of the whiteboard. Okay, and the values. Let me write I1 equals to 5 amps. I2 equals to 2 amps. Then they are separated by the distance d. I'll probably show it here. D equals to, I think, 6 centimeters. Okay, so now, if we take this line, we need to answer the question, at which point net magnetic field produced by this wire and that wire, net magnetic field, will be 0. So at any point, of course, you can take any point, and the net magnetic field will be a superposition of the magnetic field produced by this wire, by this current, and by that current. So now we need to answer the question, at which point magnetic field can actually be 0. Okay, so let me write that question. So what we need to find, a point, okay, on this line, a point where magnetic field equals to 0. Okay, let me emphasize, net magnetic field equals to 0. On this line. Yeah, exactly. So first of all, we need to find show magnetic field lines in order to see directions of the magnetic fields. All right, and then we will have to analyze this region, and that region. Right. So magnetic field lines created by an infinitely long straight wire. Magnetic field lines, of course, they form circles. Okay, let me draw a couple of them. The first one, let's say the second one. In direction cross it's into the board, so I have to position my hand like this, right, and curl my fingers around. Right. So magnetic field lines are going to have clockwise directions. Right. If you're getting something else, tell me. Right. Okay, so these are magnetic field lines. Then green. Yeah, of course, circles again. In direction, again, now I need to outstretch my thumb this way, and magnetic field lines are going to have counterclockwise directions, so this way. So now let's draw vectors in order to understand where actually zero net magnetic field is possible. So in this region, magnetic field, you remember it's tangent to the magnetic field lines, so this will be B1. Right? What about magnetic field created by the green? Actually, I can draw this one of these green magnetic field lines. It will go sort of like this, right? And direction of this magnetic field will be this way, B2. Right? So over here, I drew one of these magnetic field lines which would go, for example, through that point. So, so the question is it possible to have zero net magnetic field in this region to the left from current I1? First impression, kind of correct. It looks like, yeah, because we have B1 this way, B2 down, so it looks like, yeah, they sort of try to cancel each other. But what about magnitude? Now we need to be careful. Look, I1, current I1 is larger than I2. Okay, actually we need to, of course, let me write this formula so that I can use it. So B equals mu naught times I divided by 2 pi r. Look, so what about strength of B1 and B2? B1, since current I1 is larger, B1, is going to be all the time stronger than B2. All the time, because B2, you see, it is created by I2. I2, the value of the current is smaller. And the distance to that point, to those points, all the time is going to be larger for the second current. So, all the time, B sub 2 is going to be smaller than B sub 1, although they are in the opposite directions. But B sub 1 is going to be all the time larger than B sub 2. So, cancellation is impossible. Complete cancellation is impossible in that region. You see that? Okay, so let me write that in some reasonable words. So in this region, B net is not equals to 0. Impossible. So, impossible. And let me write, so, since I1 is larger than I2, and the distance R1 is smaller than R2. So the distance is smaller and I1 is larger, so of course B1 is going to be larger than B2 all the time. Right? So B1 is larger than B2 all the time, always. So in this region, it's impossible. Now, between these two wires, direction of the blue magnetic field, blue down, so it's a B1. And the direction of the green magnetic field, which is B2, also down. Now definitely it's impossible. Obvious, right? So since they're in the same direction, of course, they add each other. So cancellation is impossible, right? So let me write that down also. So for this region, what I wrote, B net is not equals to 0, since B1 is parallel to B2 all the time. In order to have cancellation, they must be in the opposite directions. Right? So again, impossible here, impossible there. So now the last region, to the right of the wire 1. Right? And here, again, let's look at the directions. So now also let me draw also magnetic field line produced by this current I1 over here. Right? So it will be something like this. I can do better like this. Okay, something like this. It's one of these magnetic field lines, right? So blue magnetic field is down, B1. Green, you see, magnetic field lines has counterclockwise directions, so B1 will be, B2 will be up. So opposite directions, like over here, but now let's look at the magnitudes. So B2, the current, B2 current is smaller than I1, but the distance is smaller. So distance is smaller, making magnetic field 2 stronger. Right? So as a result, balance of smaller current, but also smaller distance, it's possible for B2 to be on the same value as B1. Because B1, yeah, it's kind of stronger current, but the distance to the point in question is larger. Right? So it's possible that B2 is equal to B1. So now let's write down actually expression in order to find the distance to this point where magnetic field is 0. Right? So let's assume that this is the point where magnetic field is 0. And let me label this distance. You know what, let me use red. Label this distance, because this is our unknown, effectively, x. Distance from this wire to the point in question. So I assume that magnetic field B2 and B1, 0. I mean, they're equal at this point, and of course net magnetic field will be 0. So I assume. So let me write something like this. Assume that B net equals to 0 at the distance x from I2, from this point. Okay, so now let's write down. So B net equals 0. It means what? B net equals 0. It means that B, which way? B2 or B1? I wrote, okay, B2 at point x minus B1 at point x equals to 0. Right? So at this point, so B2 minus B1 equals to 0. So it means they're equal in absolute value. So it means B2 at this distance at this point x equals to B1 at point x. So now this is the expression which we can use to find the value of the magnetic field. So let's apply it for B2. B2, so it's a mu naught I2 divided by 2 pi. Which distance? R equals to what? Our point in question is at the distance x, our unknown. So R equals x for this B2. So times x. So now B1. mu naught times I1 divided by 2 pi. And now what's the distance? So it's a distance from this point to this point, from the point where I1 to the point where we assume magnetic field, net magnetic field is 0. So this distance consists of d plus x. You see, d plus x. Okay, so d plus x. Okay, so we have one equation and how many unknowns? Given, x unknown, given, x unknown, one unknown. So we should be able to solve it. So pretty much now it's just a question of solving it for x. So mu naught, of course, can be cancelled. 2 pi also gets cancelled, and as a result we have d plus x I2 equals to x times I1. So I just multiplied this by that and this by that. Okay, so x over here and over there, so we need to combine them. So it will be di2, and this I will move to this side. So it will be x I1 minus x I2. And of course x can be factored out. So x I1 minus I2. Just simple manipulations. So x will be this divided by that. X equals to di2 divided by... Wait. You see something? I1 minus I2, right? So I wrote x2, I2. So I1 minus I2 is in the denominator. So that's the expression for the distance at which net magnetic field is going to be 0. So if you plug numbers, we can write it in centimeters. So 6 centimeters, and then the ratio of these currents I2 is 2 amps, and divided by I1 5 minus 2 amps. Here 3, 6 divided by 3, 2, 2 by 2, 4 centimeters. It will be 4 centimeters, right? Yeah. 4 centimeters. That's the distance at which net magnetic field is going to be 0, or B1 and B2 are going to be equal in absolute value. So pretty much here, so we practiced finding directions of the magnetic field lines, analyzing their values, right, and also practice using this formula in a reasonably simple mathematical expression. Make sense? Great. So, I think it's enough. Usually students don't have significant troubles with this formula, right? Again, as I said, this is more complicated. So now, couple of, probably one conceptual question about Ampere's law. So now let's look at Ampere's law. And then magnetic forces. Okay, I will start erasing it slowly. Okay, I'll keep that for now. So number 2. So what if we have this situation, these four currents? It's more like a conceptual question, right? Not a full problem. But nevertheless, okay, so let's say current I1, then current I2, let's say here. I2 current here, then I3 and I4. So, four currents. And they all have the same value. I1 equals to I2 equals to I3 equals to I4, just for the sake of simplicity. 2 amps. Then, let's assume then that we take this loop, closed loop. Oops, we need to close it. And we need to calculate this integral. So we need to find, okay, I'll calculate, find integral of b dot ds. We just need to know the value of this integral over this loop, over a given loop, given loop. And actually, direction was also given, direction of integration. So here I drew this loop, and direction of integration is this. Okay, right, so let's say this is direction of integration. So we need to find this. So it's a basically direct application of the Ampere's law. We just need to find the left-hand side of the equation. That's it, right? So in this case, we don't need to actually integrate it. So Ampere's law, integral of b dot ds equals to mu naught times I enclosed. So that's our unknown. So we just need to find the total enclosed current carefully with proper signs. Okay, so I can erase now this. So mu naught times all enclosed currents. I4 not enclosed. Not enclosed. So we can skip it. So we have only three currents, I1, I2, and I3. So, and of course some of them must be positive, some of them must be negative. So the rule which we have to follow in order to get the correct sign for each current. So since direction of integration is given, basically this Amperian loop over this Amperian loop. So now basically we just need to use right-hand rule number 2. So you curl your fingers in the direction of integration, and your outstretched thumb gives you a positive direction for the current. So in this case, into the board, positive direction for the currents. So it means that I2 will be positive, I1 negative, I3 negative. Let me try to draw the picture, a horrible picture of my hand. 4.
Wait, hand. Thumb goes in.
In. Okay. So it means that which way I wrote it. Okay, I explained this. So this is into the page. Into the page. Because I cannot draw a three-dimensional hand, no way. Even two-dimensional, it looks ugly. So, into the page, so as a result, let me write, so I1 is negative, I2 is positive, and I3 is also negative. Okay, so now let me write over here. So it will be I2 minus I1 minus I3. Okay, so now it is equal to mu naught 2 amps minus 2 amps minus 2 amps, because all currents are the same, all currents are the same. So as a result, we're getting, it will be minus 2, probably I will use units, right? 2 amps times mu naught, in terms of mu naught. Again, the point of this question is just to remind you about this right-hand rule, how we can find, how to connect direction of the integration with directions of currents, because that's what usually students forget the first, and then the rest, with time, of course. And of course, with faculty, it works the same way. If you don't use something for quite some time, you start forgetting it. It's absolutely normal and nothing wrong with that. We remember on this something which we used almost every day. Next example, as I said, it's just basically applying Ampere's law to find a magnetic field created by an infinitely long straight wire or with the hole. I'm not going to repeat those examples, right? You can open up your notes from the lecture or from the recitation class. Pretty much there are only that type of problems which we discussed. So I don't want to repeat. If you want, here in my notes, you can look one more time of what we discussed in the lecture. Okay, enough of this Ampere's law. Now, forces, magnetic forces. First conceptually and then actual problem. Should be enough. Almost a conceptual question. So, 3. So let's do this. Let's assume that this is our infinitely long straight wire with a current I. And now I will drop a few charged particles around this wire and we will try to find direction of the magnetic force. Directions of magnetic force. So first, let's assume that this is first particle. Let's say positively charged, Q. And we want to find direction of the magnetic force acting on this particle. Right. So, application of this Lorentz force. So, we need to first find direction of the magnetic field. Because this charged particle exposed to the magnetic field. Aha. Okay, now, who sees what I forgot to draw? Very important. Without that important piece of information, my question is completely, I don't want to say stupid, but close to that.
The magnetic field?
Yeah, I will draw that magnetic field soon. Yeah, definitely. Because there is a current with the wire, so there will be magnetic field. Very important piece.
Velocity of the charge.
Exactly. You remember, I told you several times, in the world of magnetism, everything is in dynamics. In order for a particle to produce magnetic field, it must fly. In order for a particle to experience magnetic force, it must fly, it must move. So right now I just drew a particle, right, and started thinking about actually finding the force, and then I realized that essential information about our particle is missing. Velocity. Velocity must be shown. Let me look which velocity I used in my picture. That way. No, this way. So, this is velocity. If velocity were 0, what will be the net? What will be the magnetic force? 0, of course, exactly right. So, velocity is 0, force is 0. If you just take a particle, a stationary particle exposed to the magnetic field, nothing will happen. The particle will completely ignore the existence of that magnetic field. So now after this, yes, now let's find direction of the magnetic field. So that right-hand rule number 2, outstretch your thumb in the direction of the current. So and curl your fingers like this, right? So it will be, okay, let me draw. this way. So these are magnetic field lines and directions. Here it's towards us, below, away from us. So it means that I should have used different color. Okay, but anyway, realize it later. So out, here it's out of the board, out, dot. So that's B. And let me check, yeah. And here, of course, we're going to have crosses. So that's B.
Like this is
Mm-hmm.
magnetic field, right?
So this is okay. This is our wire. This is direction of the wire. I mean direction of the current towards me, right?
Yeah.
So you need to outstretch your thumb in that direction
Yeah.
and curl your fingers around, basically like grabbing it,
Yeah.
right? Yeah. So you see above, this is wire above. Magnetic field is out of the board towards you, dot.
Yeah.
Below, into the board, away from you, crosses. And so, once we know the direction of the magnetic field and direction of the velocity, now it's just a question of application of that force. So let me write underneath. So F equals Q V cross B. So now, right-hand rule first, we need to find direction of the cross product, V cross B. V that way, B is into the board, I need to adjust my body. So I have to position my hand like this. So first, along the first vector in the cross product, right? Then adjust your orientation so that you can naturally bend your fingers. Dot is towards you. So my position is wrong, orientation is wrong, I need to position like this. Right? So V, and now I can bend my fingers in the direction of magnetic field, which is towards you. V cross B. So cross product V cross B looks like down. Getting the same? And since charge is positive, so that direction of V cross B gives us a direction of the magnetic force. Right? Because again, if I position my hand like this, then magnetic field that way, no. See? Did you get the direction? Okay, cool. Right, and let me check my notes. Yes. So it is down. So F.
Just make sure that that's magnetic field, right?
No. That's magnetic force. Magnetic field is out.
Oh.
Dot.
Oh, yes.
Dot is out. It's like an arrow flying towards you. You
Oh,
see
yeah,
that?
so that's just force. Alright.
V cross B down. Okay, so next particle. Let's assume that that particle over here, let's assume it's negatively charged, and it flies up. Okay, why not? V. Okay, direction of the force. So first, direction of V cross B. V is up, B is towards you. So I have to adjust myself, I have to position like this, right? Yes, where to go. So up, V in the first vector. V cross B. So what's the direction of the force eventually? Eventually, direction of the force?
So left.
V cross B is to the right. You're right. Yeah, you're right, that way. V cross B that way. But since the charge is negative, we need to flip that direction. Right? So don't forget that about that additional step. Check the sign of the charge. Because quite often, even good students on the final exam, I saw, they make this silly mistake, right? Because they usually worry about the right-hand rule. Once they find that, they feel okay, excited, they jump to the conclusion without checking that additional small step. So let me show. So first, this will be direction of V cross B. Okay, I already forgot what's the direction. So V cross B that way. So this is the direction of V cross B, but since charge is negative, so the actual force is this way. Don't forget about that. Yeah, as I said, I will try to record it when if everything works fine. So of course, I will upload it. So now next, let's say this is positive, positively charged particle over here, plus levels. What again? Upward. So V. So again, V cross B. B is cross, it's into the board. Yeah, cross. V cross B. V cross B. So V cross B that way, and since charge is positive, that is the correct direction for the force. So this will be direction of the magnetic force. Did I get this? Yeah.
I have a question. How come for the one up top, you put your hand like this, and for the one on the bottom, you put your hand like this?
Okay, I don't remember how, but I just tried to match directions of the vectors which are involved in the cross product. Pretty much these two vectors, V and B. So first, V is up, so I just need to position my hand up. What orientation right now, I don't know. So now, in order to get the correct orientation of my hand, I need to look at the second vector in the cross product, B. So B is dot towards you. So I have to position like this, my palm that way, so that I can naturally bend my fingers in the direction of this vector B.
Oh, okay.
Direction of vector B determines, right, so orientation. So if I position like this, no way I can bend only with...
Wait, for the Q where we got the cross product, B is going towards.
B towards you in the upper part.
So I thought that V,
V.
yeah,
Uh-huh.
and then B,
B, yeah, so you're talking about, yeah, absolutely correct.
and then, but the force is going this way.
No, charge is negative.
Oh, so you flip it.
Yes, of course. If the charge is positive, direction of the cross product gives you direction of the magnetic force. But if charge is negative, your found direction must be flipped to the opposite one. Right? Okay, so over here, since magnetic field towards you, I have to position my palm this way. But here, so direction of the velocity is the same.
So it's like this.
But I need to now position myself like this and palm that way facing, because magnetic field here below into the board. So in order to bend my fingers into that direction, I need to position it like this, right?
That's it. Thank you.
Mm-hmm. So it's all about these vectors, two vectors, V and B, their directions, Okay, so now the last question. Okay, still running. So now next vector, one more, I mean not next charge. And after this it should be enough. So let's say this is our negatively charged particle, Q, and it moves this way. So finally, what's the direction of the force? Do it by yourself. And then 1 minute, and then I will do it. So what's the direction? Up, you think?
Or up.
Up, yeah. I have no idea. Of course I have it in my notes, but
For which one again? It's for.
this, the last one. So V that way, then B is into the board, so I have to orient my hand like this, right?
Oh,
So
it's
V.
into the board, yeah.
And then in order to bend my fingers into the board, I have to position my hand like this,
That's
orient.
negative. So what the force-
So V cross B is down, V cross B, but since charge is negative, up. Again, let me show in this case both directions, V cross V, and so this is V cross V, but the force, of course, will be up. Almost every exam I give questions related to this fundamental formula for the magnetic force. It's one of the foundations, part of the foundation. It should be enough. It should be enough, right? Now, make sense?
Yeah.
Great. Right. So this is basically conceptual, and now the problem. So 4, I think. Okay, so I need to draw a nice picture over here. Right. I will start with the picture, and then I will start writing actually what is given. So this is a wall. Then there are 2 springs. And over here there is a wire with a current. Current goes this way. And actually, eventually, we will have to find the value of this current. Actually, to some extent, this system which I'm going to draw can be used as a crude ammeter device, which can be used to measure current. Then, spring constants are given. Right, so let's say K, K. Okay, I will write the values. Then the whole thing is exposed to the uniform magnetic field. Magnetic field is towards you. So that's B. I think now it's time to start writing the values of all this. So we have 2 springs. Spring constants are, okay, let me write K1 equals 2, K2 equals K equals to 10 newtons per meters. Then magnetic field, 0.5 Tesla. Direction is shown. Then this wire, that part of the wire which is exposed to this magnetic field, maybe I can even, no, I don't want to outline. So this length is L. So magnetic field from this line to that line, so and the length, or the width of this magnetic field area is 20 centimeters, 0.2 meters. 0.2 meters. So what else is given? Okay, there is another thing is given, but in order to introduce that, I need to discuss the dynamics of this problem. So right now it's an equilibrium position of this wire. Equilibrium, so of course there are some forces, several forces acting on this wire. So there is a spring force, there is a spring force, but also there will be a most likely magnetic force, right? And those 3 forces gives position, they give position, equilibrium position of the wire right now. But if we, for example, turn the current off, what will happen to this wire? It will be pushed this way to a new equilibrium position. So distance from that old equilibrium position when the current was off and this new equilibrium position when the current is on is given distance. Okay, let me show this. This is, probably I'll just use dash line. Yeah. Dash line. Right, so that is let me write, so the wire is here, the wire is here, or was here, when current was equal to 0. Actually, it's basically very simple. If we turn off the current, magnetic force, of course, acting on the wire will be 0. And there is two spring forces which will push this wire to this position. So this is the equilibrium position of this wire when the current is off. When you turn the current on, the wire will be pushed that way because of the magnetic force, and this is a new equilibrium position for the wire when the current is not 0. So this distance, delta x, is given. So delta x, what's the value? 1 centimeter. So this distance is delta x, and that delta x is 1 centimeter. Of course, at some point we will have to convert it into meters, but that will be later. So this situation. Now I gave you everything, and again we need to find the value of the current. Again, let me check if I give you everything. Yeah, let me write what needs to be found. So find I. We only know about this current, direction of the current. Maybe you connected it over here to the battery, so you know here positive electrode, negative electrode, so basically you know the direction of the current. You just need to know the value of this current. So of course, where to start? And we need to start from something fundamental. And then we will start diving deeper and deeper, and we will eventually, eventually current will pop up. So, does this problem remind you of anything from Physics 1, at the end of Physics 1, where you solved problems about static equilibrium? Do you remember fundamental equations which you used in order to start solving problems about static equilibrium? Usually students don't remember at this point, but of course once I see James kind of nodding, he knows, right? Okay, I believe that. So, let me push you to the correct formula. Actually, you all know that. Which law can be used to find, or okay, not to find, to describe motion of any classical mechanical system? Which fundamental law can be used to describe motion of any classical mechanical system? Again, the Disney world of quantum mechanics is completely different, so we're not discussing that. It's completely weird, right? So, classical mechanics only. Which law? And you all know that law. You know? You do know, actually.
F equals ma.
Newton's second law, F equals ma, sounds so kind of diminishing. You need to glorify it's a Newton's second law, right?
Okay.
Equation of motion, right? F equals ma, it sounds solid. So yeah, Newton's second law, F equals ma. So let me write it down. So that's the beginning. Motion of any system can be described by, net force acting, net force equals to m times acceleration, right? Now, can we use this law to describe no motion situation? Why not? What is no motion? It's a special case of a motion, right? So what do we have to adjust in our Newton's second law in order to describe no motion situation, stationary situation? If something is stationary, if I'm staying, what's my acceleration?
0.
0. Of course, that's it, right? So for no motion, acceleration equals 0, and we're getting that beginning of the solution of any static equilibrium problem. That's what you've done in Physics 1 at the end of Physics 1 many times, stabilizing some beams or ladders against the wall, or signs, right, hanging from somewhere, right? It's all from the Newton's second law. So, in our case, of a static equilibrium, okay, of an equilibrium, acceleration equals to 0. So let me frame this is important, right? So as a result, we come to the beginning of the solution. That's the beginning of the solution. So right now, current is not even close to us, right? But that's the beginning, and we start diving deeper and deeper and deeper, and at some point, current will pop off. And only then, when everything will be revealed, we will start seeing what can be done. But for now, yeah.
So it says in our case.
In our case of an equilibrium. First I thought about writing something different. Acceleration equals 0. So that's the beginning. So now you understand what needs to be done. We need to identify all forces. And since forces are vectors, let's introduce coordinate system. Because we need to know which forces are positive, which forces are negative. All right, so let me introduce coordinate system. This is x. And I will position origin at the point where the wire is when the current is off. Okay. So now, let's identify forces. Spring force. Springs are compressed because they are not compressed when the wire is here. So right now, springs are compressed. So there will be two spring forces acting this way. F spring and F spring, because we have two wires. What did I say? Two wires. Two springs. Sorry, guys. Two springs, because there are two springs. Sometimes there's a decoupling between my brain and my tongue. It happens. All right. Then, what about something else, another force? Magnetic force. If there is a wire with a current exposed to the magnetic field, then of course there will be magnetic force acting on the wire. We have straight piece of wire with current exposed to the magnetic field, of course there will be magnetic force. So what's the direction of that magnetic force? We need to look at the cross product. F, you know what, let me write down underneath. So F magnetic, I, L cross B. Spring force easy, right? So let me write F. Spring equals to, minus Kx. So let me write absolute value, because we will discuss K delta X. Absolute value. We see the direction. So now, direction of the magnetic force. What determines direction of L? Direction of the current, right? So since current is down, so that's the direction of L vector. Absolute value of L, it's this L, right? That part of the wire which is exposed to the magnetic field. Right, so now let's look at the cross product. L cross B. L is down, B is dot, it's out. Dot is out, yeah. So L cross B, right? L down, B towards you. So magnetic force is that way. And in this case, there is no additional step because current can be only positive, right? It's not like in this formula, Q with B, we were checking the sign of the charge. Here, current is absolute value of the current in this formula. So, you getting that way? L cross B?
So L down.
L down.
So that means
B is that way, so you have to position, yeah, exactly. So your thumb gives you that direction.
See, that's magnetic force.
Magnetic force acting on this wire. So magnetic force, and actually it makes sense. F magnetic, because when you turn this current off, this magnetic force disappears, and these two spring forces will bring this current to this position. When you turn that on, magnetic force will push the wire to your left. It makes sense. That direction makes sense completely. Right? Okay, so now direction to the left. Now let me write absolute value of the magnetic force. I, L, B, and sine. Sine of which angle? Sine of the angle between L and B. Direction of L, down, B, out. The angle? 90 degrees. Sine of 90 degrees is 1. So it will be just absolute value, ILB. Okay, so we have absolute value of the spring force, ILB. So now let's write down explicitly in a vector form, and then I will take care of the directions. So first in the vector. It's outside. So right now it's just in the vector form without showing any pluses and minuses. And now let's write down relative to this x direction. So this force that way positive, this force also positive, but the magnetic force, since it points that way, negative x direction. Again, one-dimensional force is negative, it just means it points in the negative x direction. Right? Positive, it means it points in the positive x direction, or y direction, whatever directions you have. So it will be F spring plus F spring minus F magnetic equals to 0. Now I wrote explicitly all those forces with the correct directions. Again, this is negative because you see points in the negative x direction. Okay, so now we have absolute values, so let's plug it. K delta x plus K delta x plus, not plus, sorry, you didn't see this, minus I L B equals to 0. So now current appears, which we actually need to find. So now everything is in front of us. So let's analyze how many unknowns. K given, delta x given, current is our unknown. L is given, B is given, one equation, one unknown. So now we just need to solve it for current and the problem is solved. Right? So from here, ILB equals to 2K delta x. I just move this term to the other side. Minus turns into plus, and added these two terms, 2K delta x. Right? Okay, so finally, current equals to 2K delta x divided by LB. So that's the algebraic expression. And of course, if you plug numbers, okay, I will write it down by 2 times 10 newtons per meters times delta x, 1 centimeter, it's a 10 to the power of minus 2 meters, right? Yeah. Divided by L, 0.2 meters, and B, 0.5 Tesla. Okay. I'm not calculating. I will look at my notes. 2 amps.
How'd you get delta x again?
Delta x, it's a spring force.
Yeah,
A spring force, you remember from physics 1, K delta x?
very familiar.
Yeah, very familiar. So if you have a spring attached to the mass force, just a spring. If you compress it by delta x, your hand will experience the force equals to the spring force, which is equal to spring constant K times delta x. Delta x, it's a compression of the spring. So here, at this position, when the wire was over here, springs were uncompressed. And if you move it here, so springs are compressed by delta x. It's a physics 1. K delta x, absolute value of the spring force. Potential energy, 1 over 2 kx squared, K delta x squared. It's physics 1. It's essentially like a mix of physics 2 and physics 1 problem. Hmm? Yeah.
Can you explain why the FM's going that way again? 'Cause I don't.
Which force?
The
FM?
Yeah.
Okay, so, here, okay, let me frame this.
Because I thought it was going to the right.
Okay, let's see. Direction of FM is in the cross product L cross B. L, direction of L, is determined by the direction of the current. Current is down, we know, so L vector L is down. Of course, absolute value of L is this part of the wire exposed to the magnetic field, another thing, right? So direction is down. B is dot towards you. So right hand rule now, L down. Then I need to orient, actually this is the right orientation. In this, with this position I can bend my fingers towards the vector B, which is towards you. L cross B, and you see, thumb is that way.
Okay.
And it must be that way because spring force, both spring forces that way, in order for this position to be an equilibrium position, this force and these forces must be in opposite direction, right? Because then they must balance each other out. Yeah,
Can you explain where the sine 90 comes from?
this.
Yeah.
Okay, cross product. Let's say A cross B equals to absolute value. It's an absolute value of A times absolute value of B times sine of the angle between them. By definition, cross product, absolute value of the cross product.
And it's always going to be sine?
Always to be what?
It's always going to be sine?
Always, it will be it is always sine. Because it's a, what?
Or go on? It's always sine?
Always sine. Basically, it's just a mathematical tool which mathematicians introduce for us so that we can explain directions of the velocity, to explain these phenomena.
And then,
So it's, yeah, by definition, all the time, if you see cross product, it's a sine. If you have a dot product, then cosine function.
and
Dot
how
pro-
do you know it's 90 in this case?
Because, again, as we discussed, right, so L, vector L, is down. It's the direction of the current.
Uh-huh.
So L is down, B is towards you. You see B? Dot towards you.
Okay. Alright.
You see?
Yeah.
90 degrees. L, B. Okay, anything else? Awesome. Awesome. Alright, so next, let's move to Faraday's law. So we practiced this formula, this, now Faraday's law, and let's move. Again, there will be first conceptual question and then big problem. And that problem I think I gave once on the final exam. Can I start erasing? Okay, I think I will start erasing this. That's 5. Conceptual questions. So let's say we have this uniform magnetic field. Space for more. Right. So that's B. And let's take a few loops. The first loop is going to oscillate like this. Basically, if you attach it to the string. And let me draw it like this. So let's say this is the ceiling. And here there is a chord. And our loop oscillates like this. That's the loop, conducting loop. and it oscillates back and forth. So we need to answer the question, are we going to get any induced EMF and induced current?
Let's see.
So let me, all right, so we need to answer the question about the induced current. So something not clear about the picture?
Yeah. What does it say? C with the C.
Conducting loop, C-O-N-D. Yeah. Conducting loop.
Are any of those circle X's, or are they all circle dots? The
Circle, no, only dots, circle dots, no crosses.
Okay.
Right. So it's all magnetic field towards you.
Okay. Just making sure.
Okay, there are too many of them to draw, so I'm a little bit sloppy in terms of circles. Right. Okay, so in order to answer this question, so let me say this is part A, for example. Right? So let's say A. Right? For part A. So in order to answer this question, of course, we need to analyze magnetic flux to see if magnetic flux changes in time. If magnetic flux changes in time, then of course EMF is produced and current will flow through the loop. In this case, so what about the flux? So flux consists of three parameters, B, A, okay, let me write, so flux in case A equals to B dot A, so it's a B, A, and cosine of angle between them. So one by one, what happens to the magnetic field? You know what, now I realize that A, we have a vector, and here A, you know what, it's not the best option. So let me use case 1, for example. 1. Okay, yeah, it's Rome 1, it's not. So what happens to the magnetic field as this loop oscillates? Nothing. Magnetic field is uniform, right? Well, of course, we assume that there is no border over here of the magnetic field. Right? So magnetic field is constant. Then area of the loop. As it oscillates, area of the loop doesn't change. We don't distort the shape of the loop. So area is also constant. Then angle, theta. Of course, I can pick area vector, for example, in the same direction as the direction of the external magnetic field, so the angle will be 0, anyway, constant. Theta is 0 degrees, constant. So as a result, flux is constant in time. Flux equals to constant. As a result, EMF is going to be 0, right? Because, yeah, EMF equals minus d phi over dt. Okay, actually, let me write it down. So EMF equals to minus d phi over dt. So as a result, it's 0. No EMF, no induced current in this situation. So situation 1, no induced current. So we can say that I induced equals to 0. So it's the first situation. Now, second. Right, so let's say we have a spring, and over here there is a loop. Again, conducting loop. So this loop moves up and down, oscillates up and down, up and down. So it will be the same. So it moves up and down. Magnetic field will be constant. Let me write over here a second situation. Right? So that is the second case. Magnetic field still constant. It moves through the magnetic field. Magnetic field doesn't change. Area of the loop again. We don't distort the shape of the loop. And angle will be also 0. I can point area vector also, for example, towards you. So it will be 0. Or if it's away from you, angle will be pi, but anyway, it's constant. So again, flux is constant. So B is constant. A is constant, theta is constant. So again, flux is constant and EMF is 0, and of course I induced will be also 0. So trivial case, nothing happens in this case. You see that? Now, the last situation. I'm running out of space for the magnetic field. Okay, so let me extend my dots. So which way to it? Okay. Now, again, there is a ceiling. And now, okay, so we have this loop. And now we are spinning it around the vertical axis. So essentially it's like this. So we have this loop, and now we're spinning it. So let me write, so it's a case number 3, spinning. I think I will move over here for discussion case number 3. Again, we need to see what happens to the magnetic flux, 3 parameters, V, A, theta. Still, magnetic field, as we spin, nothing happens to the value of the magnetic field, it stays constant. Area of the loop also stays constant. We're spinning a bit, but we do not distort the shape of the loop. So area is still also constant. But what about angle? Magnetic field towards you. Let's start from this position. Area vector is also towards you, area vector, which is perpendicular to the loop, the surface of the loop. Now if I still start spinning, so magnetic field towards you. Now if I start spinning, so 30 degrees, 60 degrees, 90 degrees, 120 degrees, 180 degrees, 270, and so on, right? So as we spin the loop, the angle between the magnetic field and the area vector keeps changing. So in this case, theta is a function of time. So in this case, theta is not constant. So as a result, flux is not constant, changing. So as a result, EMF is not 0, and of course there will be I induced current, which is also not 0. So there will be current, induced current. We cannot say it's clockwise or counterclockwise, because in this case you're actually going to produce AC current. It is going to be over some stretch of time clockwise, then counterclockwise, then again clockwise, counterclockwise. But anyway, so the question was about
What does phi equal?
not equals to constant. Yeah, it's my ugly constants. Basically, I assume that you can decipher my constant, 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 not constant.
So not constant changing, right?
Yeah, not constant. Basically, it's a in parentheses. I can write changing in time, changing in time. So, conceptually questions, almost every exam, every final exam, there are usually questions about Faraday's law, because it's one of the essential laws, right? And of course we need to be somewhat familiar, somewhat comfortable with that.
This is all under Faraday's, right?
Yeah, it's all Faraday's law, right? So we move now to Faraday's law, and next will be about Lenz's rule. So now it will be still under the same problem number 5. Now let me discuss Lenz's rule. So first two situations, no induced current, but in the last situation, yeah, there will be induced current. Yeah. separated. So still number 5. Okay, so let's do this. So let's assume that we have a piece of wire. Okay, not piece, just infinitely long straight wire. Current I up. And I think something that like this there was in one of our clicker questions. And we have 2 loops. One loop is over here, of course, conducting loop. And the second conducting loop is going to be over here. Right, so the first one we're going to drag up. So velocity v. And the second, this one, we're going to drag that way. So we need to discuss induced current in both of these loops. I should have used similar diameter. It's not a crime. Probably I will label this loop A and this will be loop B. So this is case A and this will be my case. You understand why I immediately erase it. Because A we usually use for area vector, B is for the magnetic field. Okay, situation number 1. Situation number 2, loop number 2. There's different, the same symbol for different quantities in the same problem, that's too much. Let me show that this is situation number 1. So first of all, direction of the magnetic field, external magnetic field, which is created by this infinitely long straight wire. Right? So magnetic field lines, again, they form circles. And directions, thumb is up, and then magnetic field is going to be here into the board, here out of the board. In, it's a cross, out, dot. And here, cross, cross, dot, dot. So that's B. Am I right? Yeah. Getting? Mm-hmm. Okay, so loop number 1. Again, we need to see what happens to the magnetic flux. Magnetic flux, B dot A. So again, analyze 3 parameters. B, external, A, and the angle. Area, obviously, as we drag the loop that way, area stays the same. We don't change the area. Constant. Angle, we can pick area vector in the same direction as the external magnetic field. In this case, angle is 0, and anyway, it's a constant. What about magnetic field? Constant or not? I can try to confuse you. Oh, look, magnetic field. The closer we are to the wire, the stronger the magnetic field is, right? Right? Closer to the source. So, for example, over here, magnetic field, let's say 5 Tesla. If you move farther away here, it will be 4 Tesla, then 3, then 2. So it looks like magnetic field is changing. So does it mean that magnetic field changes, and does it mean that we're going to get induced EMF and induced current? I'm intentionally trying to confuse you. Right? Magnetic field changing.
Like for number 2 is like getting.
Number 2, it will be next. It will be number 2. Right? So the number 1. Look, I'm trying to emphasize on one thing. Yeah, magnetic field changes, but those changes are in space. As you move from point to the point, magnetic field changes. But Faraday's law doesn't care what happens in space. It only wants to see if something changes in time. So yeah, magnetic field kind of not constant over the loop, right? But we're interested only what happens in time. And what actually happens in time is you drag this loop up. So if, for example, at this point, magnetic field, let's say 5 Tesla, as you drag the loop up, at that point, the magnetic field will be all the time 5 Tesla because it is at the same distance from the wire, right? It will be the same. So if this point had 4 Tesla, as you move, it will be 4 Tesla all the time. Here, 3 all the time, and so on. So at every point, magnetic field is going to be constant in time, right? So magnetic field is not changing in time. It changes in space, but Faraday's law doesn't care about that, right? So we need to see only changes in the if something changing in time. So magnetic field is actually also constant, and as a result, magnetic flux is constant, and nothing happens in this case in terms of production of the induced current. So EMF will be 0. EMF equals to minus d phi over dt will be 0, and I induced also 0. So now, second loop, as Mark really wanted to jump immediately to the second loop, right? One step at a time. So again, 3 parameters. B, A, and theta. Area constant, right? So we don't do anything. We move the loop out, away from the wire. Area stays the same. We don't change that. Angle also. If you pick area vector, for example, in the same direction as the direction of the external magnetic field. So angle will be 0, and will be 0 all the time. But magnetic field, as we drag the loop away, so it will be also different in space, right? But now as we move, for example, if at this point magnetic field was originally 5 Tesla, now you move the loop out, so now it's a 4.5 Tesla, 4.3, then 4 Tesla, 3 Tesla, 2 Tesla. As we move loop away, at each point magnetic field is going down in time. Right? Of course, changes also, there are changes in space, right? But we don't care that. We're also interested in time. So in this case, magnetic field is getting weaker because you move farther and farther away from the source of the magnetic field. Of course, magnetic field is going down. So, external magnetic field is going down in time. Okay, so now Lenz's rule. So we can conclude that magnetic flux is also going down because magnetic flux is a product of B, A, and cosine of angle between them, between B and A. So now, Lenz's rule. Flux is going down. Where is Lenz? Back here. Flux is going down, so this situation. So the loop becomes supportive, like as I said, compared with that historical character, Florence Nightingale. All right, so trying to support dying things, right? So, in which way? So it will start driving induced current in such a direction so that within the loop, induced magnetic field will be in the same direction as the direction of the external magnetic field, within the loop, not outside, within. So it means that within the loop, I can draw a bunch of red crosses, be induced. In the same direction, induced magnetic field will be in the same direction as the direction of the external magnetic field. So it will be induced, the same direction as B external. External magnetic field, you see that black cross in, induced also in the same direction. Now, final step, right-hand rule. The second one. So we have loop magnetic field, induced magnetic field is cross, it's in, so it's this situation, right? In order to get this induced magnetic field, current must flow. So first I need to match that direction with my fingers. Right? And my thumb gives me this direction. So which is, what is that? Clockwise. I'm getting clockwise direction. So you see, I need to match this direction with my fingers. So I'm getting, let me check my notes clockwise. Yeah. So I induced. Again, we now looking only at the direction of the induced magnetic field. Because this induced magnetic field, since induced magnetic field is produced by the induced current, of course their directions must be connected. And we know the connections, right-hand rule. We usually use it to find the direction of the magnetic field. Outstretch your thumb, curl your fingers, but now it's a reverse situation. We know the direction of the magnetic field and we want to get the direction of the current which produced that magnetic field. The reverse situation, a reverse application of the right-hand rule number 2. Yeah.
For the number 1, since it's coming out, would it be going counterclockwise?
Oh, what do you mean number 1? This?
Yeah.
No, for the number 1 there is no current.
Oh, there's no.
Magnetic flux is constant.
All right.
The loop is happy, it doesn't, nothing happens, right? But in the second situation, since flux changes, right, flux changes, and of course the loop responds immediately. So it will drive current, in this case, to support dying flux. Right? So, conclusion, I induced current in clockwise direction. So, right-hand rule. Wait, Lenz's rule.
What does that say? R.
I mean right-hand rule, RHR. Come on, Mark, you attended all the lectures. You should be familiar with these abbreviations. Of course, these abbreviations are not universal, right? But since I defined them at the very beginning, not at the very beginning, at some point. Okay, so now let's solve the problem. These are conceptual questions about Lenz's rule and Faraday's law. Now let's solve actually the problem. And I think this problem I gave once, I think a year ago in summer. Okay, can we now switch to the problem? Make sense? So you're looking at it. Okay, now I will need the whole board, so I will place them. Should I wait? Good? You know, it's time to change this number. Getting sick and tired of 5. Now let's switch to 6. Numbers must grow from time to time. So, U-shaped rail, but with a fancy shape. Okay, somewhat fancy shape. Let me draw this picture and then I will write down what actually is given. It's still about Faraday's law. So, one side is, let me make it wider. U-shaped rail, conducting rail, of course. Then, exposed to the magnetic field. Let's say exposed to the magnetic field. Magnetic field is represented by these dots. So it's a B external. I skipped on circles, just dots. Too many circles to draw. So B external. Looks like some kind of rush on the surface of a board. Right. Now, we need to complete the loop. In the example which we discussed in the lecture, the conducting rod was kind of perpendicular. Now let me create this conducting rod. Kind of bent. So everything is conducting, and of course there is a contact over here and over there. So in this this rod can be moved, and actually we move it with a certain velocity, v. Of course, I will write down that velocity. Okay, I think it's time to start writing down what is given. So, conducting rail. So, conducting rail. Okay, let me write immediately the width. L. Conducting rail. L equals to 0.3 meters. Then magnetic field, external magnetic field, 0.2 Tesla. Velocity with which this this conducting rod is moved, v is 5 meters per second. So, velocity is given, and that's it. Yeah, just for fun, I can also give you these angles. For example, if you imagine this line, dashed line, then this angle, I can say alpha, and here angle alpha. And let's say alpha is given, for example, 20 degrees, I think. You will see it's not really important in maybe 10 minutes. So, we have a loop, you see, conducting loop. Yeah.
I just have a small question. Why isn't there a vector over the magnetic field or the velocity? I was just, it doesn't happen.
Okay, I'm still trying to understand why there is no vector. This vector sign?
Yeah. Okay.
My bad.
I wasn't sure if there was like a reason there.
Since, yeah, strictly speaking, there should be a vector, right? But I thought since I showed the direction of the magnetic field, direction of vectors, so kind of I was a little bit sloppy. But strictly speaking, yeah, the vector must be there. All right. So that's it. So yeah, there is a loop, conducting loop, exposed to the magnetic field. So pretty much it's possible that EMF is produced. We just need to analyze what happens to the magnetic flux and see if flux is changing, and if it's changing, what's the direction of the induced current. So pretty much we just need to answer the question about the induced current. So I induced. Direction and the value. So let me first rewrite, of course, Faraday's law, since it is essential in this problem. Right. In the application of this law, we usually divide into two steps. First, or maybe second, first we would take care usually of the minus using Lenz's rule. Right? And then we can just find absolute value of EMF. That's how we usually do it. So let's start first with the direction. Direction. And so we need to repeat steps which I just erased, right, for those situations. So we need to find what happens to the flux, and so we need to look what happens to the BA and theta. Right? So let's do it. B, external again, area, and the angle. Magnetic field through the loop. This is the loop. Nothing happens. It's constant, it's uniform, so it is constant. Then area. Area, what happens to the area of the loop?
Gets bigger.
Yeah. So as we move this area is getting bigger and bigger and bigger. So area getting bigger. Then angle. Okay, it's up to us. Since we have a freedom to choose any direction for the area vector, so I usually pick it in the direction of the external magnetic field. Towards you. In that case, area towards you, magnetic field towards you, angle is 0. Angle is 0. But anyway, it's constant. 0 degrees equals to constant. So if we combine them all, analyzing flux B dot A, of course, flux is getting larger and larger. Magnetic flux is growing. So loop, seeing that fact that flux is growing, of course, doesn't like it, and of course, it starts rebelling. So it will start driving a current, induced current, in such a direction so that within the loop, magnetic field, induced magnetic field, will be in the opposite direction to the direction of the external magnetic field. So it means that within the loop, we're going to have a bunch of crosses representing B induced. So over here I can write that B induced is in the opposite direction to the external magnetic field within the loop, because again it tries to suppress the growing flux. Great. So now once we know direction of the induced magnetic field, now right hand rule. Here's my loop. Okay, not a rectangular loop, but doesn't matter in terms of a direction. So induced magnetic field cross, it's into the board, right? Into the board. Into the board, so like this, right? And in order to get that direction, I need to curl my fingers like this to match this direction. And as a result, current is going to be this way, which is clockwise. I'm getting clockwise, right? Clockwise direction. Let me check. Yeah, clockwise. So this will be I induced. So we found the direction of the induced current. So as a result, I induced CW. Okay, great. First part of the problem solved. Now, magnitude, the value of current and EMF. So now here we just need to look at the absolute value of EMF. So EMF equals to absolute value of d phi over dt. So now steps will be somewhat similar to what we had in our lectures and recitation classes. Probably, yeah, let me first write down. So let me open my explanation box. Magnetic flux equals to B external times A times cosine of angle, which we already decided it will be 0, because area vector we pointed towards us, right? So dot. So it's an angle between this B external and that A is 0 degrees. So it is equal to B external times area. So again, I close my explanation box. So as a result, we'll have minus, of course, I can drop d over dt, B external times A. Area. Area has a complicated, reasonably complicated shape, not just a rectangle, right? Area, it's a, let me label somehow. Which way I label them? Let me follow my notes. Wow, that's strange. That's simple. So, point P, point M Okay. Now I realize why I didn't use A, B, C, because A is the area vector, again, B magnetic field, right? So in order to avoid confusions, that's why I'm using such a strange letters. Not the most popular. R, F, and M. This is K. Okay. K, and M.
I have a quick question.
Mm-hmm.
Why is the internal like opposite the external? Like, why is it opposite direction?
Because flux is growing. You remember that our discussion that system doesn't like changes. In this case, loop doesn't like when flux through the loop changes, right, in time. So if flux is growing, the intentions of the loop is to suppress the growth of that flux. So it will induce current and as a result induce magnetic field within the loop, so that we have this situation. External magnetic field this way, for example, induced magnetic field that way. So if area vector that way, then flux produced by the external magnetic field will be positive, but flux produced by this magnetic field will be negative. So we have positive flux plus negative flux. There will be what? Subtraction. No, if you add 5 and minus 2, the total flux will be 3. Of course, less than 5, so there is a subtraction of the magnetic flux, right?
Right.
So that's why induced magnetic field is in the opposite direction within the loop, because intention of the loop is to suppress. If magnetic fields are in the opposite direction, flux are going to have opposite signs, and there will be flux suppression. So, so before I start applying those symbols, right? So which actually symbol can be pulled out of the sign of differentiation? B. B external. It's constant, but area is not constant. Area is a function of time, so we can't extract. It will be mathematical crime, right, doing this. So I can take magnetic field and extract it because it's constant. Okay, so I can write it as B external and rate of change of the area. Right. So now let me write explicitly which area. So it's a B external and then d over dt. Our area consists of what? 2 parts. This rectangle, which is K, R, M, E. This rectangle, right? And then triangle R, F, M, and this triangle. I can divide it, right? It's not a big deal. Area is an additive thing, additive quantity. So I can write area of B, K, R, M plus area. Okay, I'm getting close to the border where I can write R, F, M. So, if you differentiate these 2 terms, these 2 areas, which area is going to survive that differentiation without being annihilated? So which area is going to survive? Of course, rectangle. What happens to the triangle? Area of the triangle, this RFM, this triangle, RFM. As we drag this rod that way, area of this triangle in time stays the same. So if you differentiate a constant value, constant area, you will get 0. But area of this triangle, this distance keeps increasing, this KR, this distance keeps increasing all the time. So area of the rectangle is growing, but area of the triangle stays the same. This area is constant, so as a result, constant, let me write over here. So dA of RFM over dt equals to 0. Right, derivative of that area is 0. So as a result, we'll have B external area of that triangle P. Yeah, that's strange symbols. M over dt. So now we need to somehow, actually very similar to what we did in the lecture, need to move away from this aerial velocity, that's how fast area changes in time, right, to this velocity, linear velocity. And in order to do that, yeah, question?
It's again about those abbreviations.
Okay, yeah.
PKRM. That is APKRM.
Which, this one?
Yeah.
PKRM. PKRM. This rectangle.
Oh. All right.
And then triangle RFM.
Oh yeah. All right. Yeah. I see.
So, how can we make a transition? So, in order to make a transition from the aerial velocity to just linear velocity, you remember the trick? We need to introduce, just for a couple of minutes, this distance, x, for example, right? Distance from this edge of the conducting loop to this point, the end of the rectangle, just for a couple of minutes. So, let me write it down. So explanation box, so let's introduce x. So as a result, that area can be written how? So how can we write that area? Area of this rectangle. If we introduce this x, area of this rectangle. L is given. Yeah. Width is given, length is given, so L times x. Right, and now, right. So it's a L times x. Okay, so I close my explanation box, and so pretty much we're almost there. So now let's write it down instead of this L times x. So B external d over dt of L times x. So now the next step, which quantity can be pulled out of sign of differentiation? The width is constant. L is constant. So this L can be extracted. So as a result, B external times L and absolute value of dx over dt. And dx over dt, how fast this x changes in time. It's a velocity. It's the velocity with which we drag basically this rod and of course these points that way. So it's a velocity. That's the velocity. So we have as a result B external L times V. So it looks like I made system more complicated. I introduced this area of the triangle, but actually from the mathematical point of view, it didn't increase complexity. It just basically gets washed out from the calculations because area is constant, differentiated. So, of course, you can plug numbers. Yeah, I will just use my notes and write down the answer. So it will be 0.3 volts. You can plug numbers and you will get 0.3 volts. It's the EMF, potential difference, volts, units of volts. So now the last step, current. So now let's assume that we know the resistance. Of course, strictly speaking, resistance of the loop changes in time because these parts of the rod are getting larger and larger and larger, but let's assume at this particular moment of time resistance is given. So now assume R equals to, what's the value? 0.1 ohms. think it's a normal value of the resistance of a piece of wire. 0.1 ohm. At this moment of time. At this time. At this moment of time. Okay, so of course, induced current. Since we know the EMF, which is somehow mysteriously produced in the loop, so you take that EMF and divide it by the resistance. So 0.3 divided by 0.1 ohm, so 3 amps. 3 amps of the induced current. Ah, yeah.
On the exam, do we have to do all the differentiating? Can we just move right to the?
No, I noticed that students like, I know, they find it easier to just remember BLV. If you write BLV, it's not something fundamental. It's not what we're testing, your ability to remember that particular formula. So what in physics, in any other science you need to remember? You need to remember some fundamental formulas, fundamental equations, fundamental principle. Faraday's law, fundamental thing. So pretty much I want to see your ability of grabbing this and getting that BLV or whatever XLV or right. So if you just write that final expression, immediately lots and lots of points will be subtracted.
So,
Yeah.
why is DAR FM DT 0 again? I want to.
This,
Why is it 0?
because this area is constant,
Yeah.
area of the triangle. So
Okay.
if you differentiate any constant quantity value, right,
Yeah.
you'll get 0.
Also, that's only the rectangle is.
A rectangle, pretty much, yeah, that's what area of the rectangle, that's what bring changes in the area of the whole loop. This triangle contributes nothing. And of course, tacitly I assume that we're not discussing that moment of time when this triangle was crossing this front line, back line, because that will be different situation, different story.
So then,
Yeah.
how does DA over DT take RF become?
Oh, because it's this rectangle. Which?
Yeah, like, and then it equals DT, it then is the external DT L times X.
I introduced this quantity x. It's nothing wrong with that.
Oh, wait, L times, alright.
Yeah. So I introduced, right, in order to make this transition smooth. Yeah.
Alright.
And so then this area of this triangle is L times x. Make sense? Yeah.
So yeah, I have a stupid question, but why is L then not 0 if it's a constant?
Because it's a product. L times x. Here we have a sum.
Oh,
Two different things, right? Apples and oranges, right? So, all right. So if you have a constant times some variable, right? So if you differentiate it, that constant stays, and then it will be equal to constant times derivative of that function, which is in this case changes in time. But if it's a sum, a plus b, and you differentiate separately first term, separately the second term, right? So different things. Here we have sum, here we have a product. Okay?
Right. So then we plug, so the external times L times V, so 0.3 meters times.
Yeah, you can plug those numbers. You will get that number definitely.
Like I'm looking at it, you plug in 0.3 and then you plug in, I know that's velocity.
Mm-hmm. 5 meters per second, so 0.2, 0.3, it's a 0.06 times 5, it will be 0.3. So that's the correct number. Okay, so the next example, you can read it by yourself and practice. Now, inductors. Inductors, so problem about inductors. Then electromagnetic wave, interference, and double-slit and grating. Yep. Okay. So first, we will discuss response of inductors, basically conceptually, response of inductors on the fact that current changes in time, and then simple problem. So now 7. Okay, so inductors. So basically I want to discuss this potential difference produced by the inductor. So 3 situations. No, let me probably start with this. Like I did at the very end of the previous lecture. So, inductor, effectively solenoid, it's a loop. No, not loop, it's a loop. It's a, if you take thousands of loops, position them next to each other, of course you will get, and a connector, of course, you will get the inductor. So, of course, various systems are very, very similar. And for the loop, we apply this length rule. That the loop doesn't like when flux changes in time. If flux is constant, then it's happy. If flux is growing, then it tries to rebel. If flux is dying, it tries to support dying flux. So pretty much, you can apply that length rule for the inductor. But as a result, you add additional steps. As a result, the analysis becomes more kind of complicated, right? In terms of number of steps, not complicated, but just a little bit more tedious. So if something is tedious, of course, sooner or later people will start adjusting those rules in order to make them more convenient for this particular system. So pretty much in this case, this length rule was transformed, adjusted for this solenoid so that it would be faster to analyze what happens to the potential difference and what will be the direction of the induced current. So as a result, the new transformed length rule sounds like this. If you have a solenoid and there is a current flowing through the solenoid, if that current is constant, then inductor doesn't do anything. The inductor likes when the original current stays constant. It wants to keep current as constant as possible. So now, if original current which flows through the inductor is growing, it's sort of like a flux, it's growing. So now here system rebelled, now the inductor will rebel also. It will rebel also. In which way? It will start driving induced current, secondary current, in the direction opposite to the direction of the original current. If original current, which is produced by the battery, right, is dying in time, then again, inductor doesn't like it, and it will start producing potential difference as proper potential difference, and as a result, induced current in the same direction as the direction of the original current, sort of supporting, don't die fast, right? So live a little bit longer. So basically, it's a physical idea, very similar, but now we're talking about current instead of flux, supporting current or suppressing original current. So now let me draw that situation on the board, what I just told you. So 3 cases. So what if we have the inductor and first, okay, L, right. So then original current, let me call it I naught. So I naught, original current. If that original, you know what, now I want to add something next to that and I don't have a space. So if that original current is constant, then inductor is completely happy and it doesn't do anything in this case. And also, since original current flows this way, so this is final point. This is effectively final point, and that is initial point, right? So we're talking about this delta V. Okay, delta V. We will discuss later. So in this case, if this current is constant, then, which way I wrote it? So if current is constant, then L does not produce delta V Okay, you know what, probably let me rewrite this delta V over here. So basically we're discussing this formula. Delta V equals to minus L di over dt. And what is delta V? It's basically V final minus V initial. So delta V is this. So this is delta V. So here it's a V final, here V initial. So if current is constant, then L inductor doesn't produce delta V across itself. Right. So as a result, delta V is 0 and delta V is 0 and I induced is also 0. Inductor doesn't produce any current. In this case, it's completely happy. And that's what you see in the formula. If current is constant, derivative is 0, delta V is 0, nothing happens. Now, next situation. Let me retreat here. So that's our inductor. Right. Again, original current. I naught, let's say, increases. And so now I usually draw this train of thoughts. So I naught is growing. As a result, the inductor doesn't like the fact that original current increases, so it tries to suppress the growth of the original current. So it will produce the proper potential difference so that I induced will be in the opposite direction to I original. So it means that I induced is going to flow this way. Okay, here there's of course, the loop is closed over there somewhere. There's a battery, right, and so on. So you see, original current flows this way, but wait, I drew the same direction. No, hold it. No, opposite. So here it's this way, and here that way. No, this is correct. So opposite directions. And now, in order to get to the conclusion, which point is at higher potential, which point is at initial, which point is at higher potential, which point is at lower. So this is final point, this is initial point. So now we need to answer the question, which point, this or that, is at higher potential. So we see the direction of the current. Of course, we know current flows from plus to minus. So it means that over here we must have higher potential, over here we must have lower potential. Or you can think of a fictitious small battery, plus, minus. So of course you can ask the question, so at the expense of what solenoid produces this potential difference? You remember how we introduced the inductors in the first place, at the very beginning. It's a device which allows us to store energy in the form of the magnetic field. Inside there is a magnetic field, so there is some amount of energy stored. Of course, it's not that great, not that gigantic amount of energy, but some amount of energy. So that's why this induced current will flow for some short period of time, but then eventually it will disappear. Okay, so in this case, as a result, we can, which way I wrote it, as a result, I can write that V final is smaller than V initial. Again, final point because the original current is exiting at this point. This is the initial point because at that point, original current enters the solenoid, enters the inductor. Right? Okay, so now the last situation, and why I'm getting into this now kind of on the lecture and the last one at the very end and here, because on the exam lots of math about these problems. When I give a question among multiple choice questions, lots of troubles over here. So now this is our inductor. This is again original current flows this way. So I naught, let's say, decreases. And of course, the inductor doesn't like it. And now, since current is dying, so it will try to support. So it will drive its own induced current in the same direction as the original current. Right? So now I naught is going down, so as a result, I induced is going to be in the same direction as I original. So it means that it will flow this way. So that's I induced. And so now again, think of this fictitious small battery. So what should be the polarity of the fictitious battery over here? So instead of this inductor, in order to get this direction of the current. So it flows from plus to minus. So here you should have plus, and here you should have minus. So it means that this final point should be at higher potential. This initial point should be at lower potential. Again, this is our final point. This is our initial point. Again, why I started introducing this fictitious battery? Because quite often I saw in the past students, when I drew, for example, here plus, here minus, and students know that current should flow from plus to minus, and they draw, and they sort of think that induced current flows this way, from plus to minus. No, this plus and this minus is produced over here, and then that induced current flows to the rest of the circuit. This is the produced in the solenoid. This whole thing produces plus and minus, and then induced current flows to the rest of the circuit. So now, as a result, what's the potential? V final is at higher electric potential than V initial. Here it was at lower, here higher, because induced current. So first you look what happens to the original current. Then as a result, you can immediately jump to the conclusion about the direction of the induced current. And once you see the direction of the induced current, of course, you know it flows from plus to minus. You can get to the conclusion which point is at higher potential, which point is at actually lower potential. It's very similar to Lenz's rule, just adjusted. Okay, so maybe I can give you I've been standing and thinking, maybe I'll give you quickly some imaginary situation in order to see if you're getting this. So let's assume that we have an inductor. And let's say this is the original current, like this, I naught. And let's say this original current is growing. I'm just making it up, I have no idea. And so we need to answer the question, which point is at higher potential and which point is at lower potential? So this is our initial point, this is our final point. So which point, so what can we say about V initial and V final? So which sign should I put between them? Larger, smaller, or equal? So analysis is this. Original current is growing. Inductor doesn't like it. So of course it will increase. It's this situation. So it means that the induced current will be flowing in the opposite direction relative to the original current. So original current goes this way. So it means that the induced current is going to flow that way, right? Okay, so I can complete, right? Because over here somewhere there is the rest of the circuit, right? So that will be the direction of I induced. I induced. So now, again, think about fictitious batteries. So in order to get this direction of current, positive electrode must be on this side, negative electrode must be on that side. So it must be plus, minus. So it means that this point, initial point, is at higher potential, we see plus plus, and here the lower potential. So it means that V final is over there. V final is at lower potential than V initial. So I'm getting like this, right? Again, let me analyze. So it's a opposite directions. So it's a plus minus. So it is a initial. Yeah, that's correct. Or maybe slightly twisted situation. Response of the solenoid can be given, for example, plus or minus, and you need to answer the question, what happens to the original current? Very similar analysis. You see the polarity, you see what inductor produces. Again, think about the battery. Draw the direction of the induced current and see if it's in the same direction as the original current. It supports. It means that. What was the question? Yeah, what happens to the original current, right? So if it is in the same direction, it means that original current decreases if induced is in the same direction. If induced current which you draw is in the opposite direction to the original current, so it means that original current is increases. So almost every semester I give questions like this on the exam, and maybe like 30 or 40% of students' answers are wrong. Right? So that's why I decided to bombard you with this. Right? Okay, so what? Almost getting close to 2-3 hours. Let me just quickly check this. So you know what? The problem which I was thinking about solving, you just need to inductance is given, so the rate of change of current is effectively given. Let's skip it. You can read it by yourself. Right? It's my major. What I worry about this conceptual analysis. These problems usually very, very simple. You can crunch those numbers by yourself. Right? Reading. So after this, electromagnetic waves, basically traveling waves, electromagnetic waves. Take it that. Okay, so I'll start erasing this. And again, based on my experience, students most of the time do reasonably well with electromagnetic waves, except for 2 parts, and of course I will emphasize on those parts. Wait, what is the number?
8.
Now 8, well. So, EM wave. So what do we know about this electromagnetic wave? Propagates in z direction. Propagates in, plus z direction. Then, electric field points in the x direction. Okay. So we'll have to write E as a function of, I don't want to write immediately, because I will write the answer immediately, part of the answer. So let me write math expressions of E and B. Okay. Another thing, frequency is given. F is given, 60 Hertz. Sorry guys, I don't know why I picked such a low frequency, because as a result, wavelengths will be really scary, gigantic, really, really huge. But again, it doesn't matter. It's still possible, it exists in the nature, so not very common maybe. Right, so let me first write this expression without knowing K and W, right, in order to analyze directions of directions. And you know what, even before I start writing that down, let me draw the picture. So, this axis, it propagates in a z direction, so this is z. Then, of course, let's pick a right-handed coordinate system. Right-handed, it means if you take a cross product of x and y, you should get z direction. So in order to get x cross y and in the z direction, so this should be x and this is y. So x cross y, you will get positive z direction, so a right-handed coordinate system. So electric field oscillates in the x direction, so electric field oscillates up and down. So let me draw it. And it's a sine function, so let me use sine function, so it will be something like this. So that's electric field. Then, magnetic field. What's left for the magnetic field? Which direction is still unused? Y, right? So because you remember, these three directions, E, B, and V, they must be perpendicular to each other. So velocity in this way, V, E in the x direction, so magnetic field must be in the y direction. So that's magnetic field. So B. So that's the picture, and now let's actually start writing down mathematical expressions. So let's start with the electric field. So E equals amplitude. On purpose, I'm skipping some very important steps because I want to discuss that. Okay. Okay, enough. Too many gaps. So first, subscript next to the electric field. Which subscript should be used here? Should we write here? That's the first place where lots of troubles, lots of mistakes. In this case, actually, it's written electric field oscillates in the x direction. Electromagnetic wave is a transverse wave. Sort of like a wave on a cord. Wave on the cord propagates, let's say, in the horizontal direction, but particles moves up and down, up and down. So the same with the electric field. Electric field up and down, but the wave propagates in the z direction. Electric field oscillates in the x direction. Over here, we must put x. It's a first place for lots of mistakes, right? So but the wave propagates in the z direction. So k. So now which variable we have to write over here? Of course, z, right? Z. It's the direction of wave propagation, z. Then plus or minus. Minus because it propagates in the positive z direction. So minus. So omega and time, nothing special about time. Time doesn't have any directions, so it moves only forward. Then initial phase, this initial phase. You know what, guys? Most of the time when we work when we work with electromagnetic wave, most of the time we're not interested in the initial phase, right? So usually it's a fast oscillating waves, right? And usually in experiments, we're not interested in the initial phase. Although it's still possible situations where you might be interested in the initial phase. All right, so here, let's assume we don't care about the initial phase. It's zero. At the initial moment of time, the wave goes through the origin. Initial phase is zero. Actually, additional question which I forgot to ask. Is this a history graph or snapshot graph? It's effectively a photograph of the wave. If we could take a picture of an electromagnetic wave. So you see we have Z. It's a snapshot graph. It's a snapshot graph. Let me write that down. So it's a snapshot graph. Oh, for example, let's say taking at t equals 0 to justify that there is no initial phase in my mathematical expressions. Now everything matches. Great. So now, what about magnetic field, B? And now subscript must be y. B sub y equals to V naught. And as I said at the very beginning, both of these waves, electric field traveling wave, magnetic field traveling wave, they oscillate in unison. So it means that Z and time dependence in this case exactly the same. So you just, if you have an expression for the electric field, for the magnetic field, you just need to rewrite this here. Just copy and paste. So this part, sine kc minus omega t, is exactly the same over here. All the time. So sine kz minus omega t. So this part, exactly the same all the time in the electromagnetic wave. So pretty much differences only in the subscripts, amplitudes, and of course instead of E you need to write B. Okay, so now electric field amplitude is given. We will have to find B naught, we need to find K, and we need to find omega. Basically 3 parts. And that will be the end of the problem. So let's start with K. So by definition, K it's a 2 pi divided by lambda. Wave number, K is a wave number. By definition, 2 pi divided by spatial periodicity. But do we know the wavelength? Not yet. Actually, the wavelength over here, it's just, because it's a snapshot graph, so this is actually lambda. This is lambda. Okay, so, but we know it's electromagnetic wave. Although kind of low frequency, but electromagnetic wave, and it propagates with the speed of light. We know speed. We know frequency, so we should be able to find wavelengths just like that. So, since V equals to lambda f, and of course V equals to the speed of light, so of course from here we can get lambda equals to c divided by f. Now I will plug numbers and don't get scared because the wavelength is going to be really gigantic. Okay, low frequency 60 hertz electromagnetic wave, really gigantic wavelengths. 3 times 10 to the power of 8 meters per second divided by 60 hertz. Okay, hertz, it's 1 over seconds. Okay, let me use my notes. So it's 5 times 10 to the power of 6 meters. Don't try to imagine it.
660, what is that?
61 over seconds, hertz.
Oh.
Right. Just in order to see seconds, cancellation of seconds. So it's a gigantic velocity. Oh, it's wavelengths. All right. Okay. So now, once we know wavelengths, of course, we can find k. K equals to 2 pi divided by 5 times 10 to the power of 6 meters. I think I used
That's the length, right? Wavelength.
wavelengths here. Lambda wavelength. It's almost like a universal convention. Wavelengths, lambda. So it will be 1.26 times 10 to the power of minus 6 inverse meters. So that's the wave number, spatial frequency, effectively wave number. Okay, we found K. Now, next, omega. So let me probably put here the first bullet, K. Now, what about omega? I would probably start again from the definition. We introduce K and omega in a very similar way. So omega equals to 2 pi divided by t. Period is not given, but we have frequency. And they are reciprocal of each other, t and f, right? So of course we can write it as 2 pi f. 1 over t, it's f frequency, right? So pretty much we just need to plug numbers. I don't need to know 60 hertz, so it will be 120 pi, or maybe, yeah, actually calculate. So 2 pi times 60 hertz, so it will be 377 radians per second. So what's left? What's left? B naught. Amplitude of the magnetic field. Amplitude of the magnetic field. So B sub 0. We just need to remember that amplitudes of the electric and magnetic field are deeply connected through the speed of light. Electric field is electric field amplitude is way larger than magnetic field numerically. 8 orders of magnitude. So we just need to remember that E naught equals to C times B naught. Again, it can be shown mathematically when we move, if you move from the Maxwell's equations to wave equations. But we skip that. I just told you that these amplitudes are connected to the speed of light. Okay, so we need to find B naught. So it's a electric field amplitude divided by C. So it's a 20 volts per meters divided by 3 times 10 to the power of 8 meters per second.
Isn't it 2?
2? Oh, yeah. I don't know where I get 20. It's evening, Friday evening. I saw it somewhere today, some 20 somewhere. Okay, maybe in the previous program.
That's
Come on,
2
some interferences in my head happens.
2 volts per meter, or was that 2 over,
Volts per meters.
yeah, volts per meter.
Yeah, it's good. Correct. All right, so, okay, the answer is going to be 6.67 times 10 to the power of minus 9. Okay, units of Tesla. Of course, we know that you will end up with Tesla. So, that's it now. We just need to write down the expression. But you know what? We found everything, so you just need to plug the values. Okay, problem solved. Right? So just rewriting this with the numbers, it's waste of time. But of course, if the problem asks, write down in terms of, no, actually I would never subtract the points. If you find everything and write in the symbolic form without plugging numbers, yeah, I can buy it. Okay, so now, problem about interference, it's not complicated, it's not as lengthy as the previous one. We should be able to finish within 4 hours. Okay, can I start erasing this? Right. Also, it's possible that problem of this type can be about acoustic waves. No, probably I wouldn't have acoustic waves here. For interference, yes. So that will be 9. So problem number 9. Interference. So let's imagine this situation. We have, okay, let me write 2 out of phase radio antennas. Okay, why not? Radio antennas. Speakers easily possible with acoustic waves. So let me draw these pictures. So we have antenna number 1, antenna number 2. Okay, let me use different colors. Right, so this will be, okay, this is number 1. This is number 2. Frequency is given. F equals 300 megahertz. Prefixes are now usually given in the formula sheet. Mega 10 to the power of 6. So, of course, this antenna produces its own circular waves. If you look at the cross section, of course, these are spherical waves. Then, blue first antenna produces its own circular waves Of course, since they are identical, we assume the same amplitude, frequency is the same, wavelength is going to be also the same. So two identical waves. So of course, these two waves are going to interfere at every point, right? So constructive, destructive, constructive, destructive, destructive, constructive, right, and so on. So a particular point is given. A particular point. Okay, just this for example. So this distance R2 equals to 5 meters. So pretty much I removed all the geometry. I gave you immediately R2, R1. So this is R1 equals to 2 meters, for example. Right, and out of phase, so let's say that initial phase of this second source is phi 02 equals to pi, and phi 01 equals to 0. It's written the out of phase, so for example, I think 2, 0. I mean pi 0, sorry. So now the question is constructive or destructive interference at that point. So over here somebody standing, right, detecting those net electric field, electromagnetic field at that point with some antenna.
So just saying those some P
Pi, phi
phi
02, phi 01. It's initial phase of the first wave and initial phase of the second, the first source and the second source. And yeah, initial phase of the wave, it's also correct.
so wait, C.
What? 2 out of phase
Yeah.
antennas. Good? Since you're not in my recitation class, that's why
Yes.
you're not familiar with my handwriting. Right. Okay, so it's all here, nothing else. We just need to find path length difference and inherent phase difference. So in the problems of this type, it's nothing but that 2 pi over lambda, and of course it's given in the formulation. 2 pi over lambda times the path length difference plus the inherent phase difference, and if it is equal to m times 2 pi, then in that case we're going to have constructive interference. If you have m plus 1 over 2 times 2 pi, then destructive interference. So let's just quickly calculate delta r, delta phi naught, and what else is missing? Wavelength. Frequency is given, wavelengths we'll have to calculate. So delta r, R2 minus R1, path length difference. So 5 minus 2, so 5 meters minus 2 meters. Of course, on the exam, usually I give some geometry, so you can apply Pythagorean theorem or something like this. But here, in order to save some time, so I decided to give this R2 and R1. Actually, it's a problem from one of the quizzes a few years ago. I used it. How I like this. It stops recording sound at some point. So then delta phi naught. Out of phase, pi. If the problem says in phase, then inherent phase difference will be 0. Again, you remember we discussed it in our recitation classes, right? So basically, most of the time, that information about the inherent phase difference is either in the statement of the problem, or maybe sometimes initial phases are given. Initial phase of the second and the first wave, just subtract them in order to get the inherent phase difference. Right? So 3 possible situations. So in this case, delta phi naught is pi out of phase antennas. Basically, it's given in the problem. Okay, so now what's next? Wavelengths. Since it's electromagnetic wave, radio antennas. So we know it propagates with the speed of light. And I saw several times on the exam, for example, instead of radio antennas in radio waves, I give two speakers and acoustic waves, and still maybe 5% of students, they still use speed of light. Yeah, so don't use speed of light with acoustic waves, right? In that case, I usually give the speed of light. Speed of sound. It's usually about 340 meters per second. It depends on the temperature of air, but usually I try to give those numbers. Yeah.
Sorry, I can't read what it says next to CD on the left side of it.
This,
Yeah, what it says right next to it on the left.
The person.
the person.
Oh. sorry.
Come on, it's a cute person
Yeah.
with antenna standing.
Antenna.
Yeah, I see.
Maybe okay. Wow, how did you manage to see some words? Wait. No, my handwriting is not that bad. No, it's a person, right? See it?
Yeah,
Okay. Okay. Yeah, wavelength. All right, so wavelength equals to C over F. Speed of light. So 3 times 10 to the power of 8 meters per second divided by 300 times 10 to the power of 6 hertz. It's 1 over seconds. It's 3 times 10 to the power of 8 and again 3 times 10 to the power of 8. So we're getting 1 meter. Really? Oh, what's a nice number. Yeah. Yeah, it's on purpose. I remember it was on a quiz. I gave it on a quiz a few years ago as a quiz. And so, of course, I usually try to prepare numbers as nice as possible. Yeah.
Making sure again, hertz is 1 over
Yeah.
seconds.
Yeah, 1 over seconds. So 1 meter. Okay, so now we just need to plug them in our expression. So delta phi. So 2 pi divided lambda 1. Then delta r 3. I'm just writing down the condition. Delta phi naught pi. And so what are we getting? Meters cancelled, so we're getting 6 pi plus pi, 7 pi. Constructive or destructive? We got 7 pi. And so what we have? This is constructive case, this is destructive case. In my recitation classes at this point, I usually give a pause, right? So students, to hear students, right? Because quite often, at this point, the student jump to wrong conclusion. They see, looks like it's a simple expression, and out of these two, this looks simple. So they jump to the conclusion that it's constructive interference. And of course, it's a wrong conclusion. Because we have odd number of pi's. In this case, in the case of a constructive interference, if you take any integer, multiply it by 2, you're going to get even number of pi's. And we have odd number of pi's. So constructive interference is impossible. It's only possible, most likely, with this. So let's just check it. Let's just check it a second. So m plus 1 over 2 times 2 pi. So which m should work, will work? 0, no, it will be pi. 1, it will be 2 over 2, it will be 3 over 2, it will be 3 pi. 2, 4, it will be 5 pi. 3, 6 over 2 plus 1 over 2, 7 over 2 times 2 pi, it will be 7 pi. So m, it corresponds that spot corresponds to a destructive interference corresponding to integer 3. So that's destructive interference. So if you step away somewhere in certain direction, it will be constructive, then again destructive, then again constructive, destructive. So basically you have infinite number of bright and dark spots. Constructive points with constructive and points with destructive interference. So, couple of conceptual questions under this, and although we discussed it in our recitation classes, so it should be fresh in your heads, right? So what if we have these two waves? So plane waves. It's not plane. So two waves with these wave fronts. So this is the first one. Then let's say this is the second wave propagating this way. And let's take a few points and analyze in terms of them being constructive or destructive interference. So let's take, for example, this point, right? Point A. Constructive or destructive? In this case, we don't need to do any calculations. Or the question can be about, let's say, amplitude of these two waves, I don't know, 2 millimeters. And I can ask, what's the amplitude of the net wave, resultant wave at this point? What will be the amplitude at that point A of the net wave? 4. Look, we have crest. Okay, this is, you remember what does this line, what do this line mean? These lines are wavefronts, collection of crests, right? So we have wavefront of one wave, wavefront of the second wave, right? And so pretty much it means that we have crest over crest at point A, so we're going to observe constructive interference. Constructive interference, what does it mean? It means that you have two waves, let's say the first wave and then the second wave, right? So crest over crest, amplitude of course gets doubled, doubling amplitude. So if we have, for example, amplitude of these two waves 2 millimeters, so if the question is about what's the amplitude at that point, of course will be 4 millimeters, right? So, but in this case, I decided just to ask, is it constructive or destructive interference? So, constructive. Then, let's take this point, for example, this point, point B. Constructive or destructive again? Huh?
Destructive?
Careful. So what do we have? It's a between wavefronts. So it's a trough. Then between wavefronts, again trough. So if essentially we have trough over trough. What is that?
Constructive.
Constructive. So essentially it's a what? Crest over crest or trough over trough. What a big, it's the same. Right? So crest over crest, trough over trough. Right? So point A, we were here. Point B, we are here. It's still doubling amplitude, still constructive interference case. So point B, still constructive. And of course, if the question about what's the amplitude, if for example 2 millimeter amplitude of both waves, then of course the amplitude of the resultant wave is going to be 4, for example. Then, what if we take, for example, this point, C, and again, okay, you understand different meaning of C's. So what about this point? We have wavefront of the blue wave, it means it's crest, and it is between wavefronts of the black wave. So we have crest over trough, complete cancellation. Right? So basically it's this situation. So you have blue wave, and then on top of that you have green wave. So basically we have our case, crest over trough. Of course, the resultant wave is going to be zero disturbance. So at point C, of course, we're going to observe destructive interference. So pretty much you just analyze lines. So if it's a line over line, crest over crest, constructive. It's a trough over trough between lines, again constructive. But if it's a between lines and the line, of course, that is a destructive case. And if you don't remember, so how can we get these plane waves? It's essentially what? If you have over here, for example, circular waves. If you let them propagate to infinity, basically the radius is going to be so, diameter is going to be so gigantic of these circles. So you're not going to see any curvature. Basically you're going to see straight lines, bunch of straight lines. So wavefronts. So essentially the same. Okay, so that's what I have here. Okay, so the last couple of problems, and we'll call it a day. So check it's still charging. Cool. So this problem I used to discuss in the past in the recitation classes. So let me erase this. Yeah, here are. Is that your piece of paper or not? Ah, no, I meant on the chair. Right. So, double slit. So the last two sections. So now double slit system. I will probably draw the picture and then I will. Okay. Let me change the marker using contrast. So that's actually essentially the same. I know these new markers, which our department bought, don't have enough contrast. So screen, double slit, then distance to the screen is given. Okay, so it's a double slit, and this is the screen on which we observe interference pattern. So L is given. L is 3 meters. Then, of course, we need to use laser light, right? Wideband source wouldn't give us interference fringes, laser. So 633 nanometers. So it's a laser. So we illuminate this double slit with the laser. Then we need to find eventually this distance between slits, D. Again, as I explained to you, situation where this can be seen in photonic center of any optical company. You fabricate something and then you want to check using optical setup if actually what you fabricated is what you were planning to get, right? So you create the scratches, create double slit, and then put a simple optical setup and illuminate with a laser, observe interference fringes, and calculate the D. It's very, very typical situation in research. So, center. And of course, as you know, we're going to observe here a bunch of bright and dark spots. So, now, Of course, you can, for example, use, I don't know, bright spot number, I don't know, 1 or 2, measure the distance to that bright spot, and using the formula which we derived, this formula, of course, you can calculate D. But the thing is, in these double slit interference fringes, distance between bright spot and the size of the bright spot, they're kind of comparable. As a result, it's not that, you cannot measure those distances accurately. So, what can be done in order to increase accuracy, right? They reduce the amount of, they reduce the error. You can, for example, measure the distance not between two bright spots, but between, for example, as much as you can. In that case, you can increase the accuracy. So in this problem, somebody measured the distance between 12 bright spots. Just somebody counted, okay, so this is first counted 12 bright spots and measured the distance between them. And using that information, decided to calculate the distance between slits. It's just a very possible situation to increase accuracy of your measurements. Right, so as a result, let me count 12. So this is the first, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whew. So this distance somebody measured. And that is 52 millimeters. This distance A equals to 52 millimeters. And number of slits over here, number of bright spots, 12. Okay, so I think that's what is given. And we need to find the spacing between slits. So we need to find D. So it's all about, of course, this formula. Let me rewrite it and analyze what is good and what is not good. M lambda L over D. So that's what we derived in the lecture. Right. Basically, Ym, it's a distance from the center of the screen to the bright spot number M. Y1, Y2, Y3, and so on. Right? But we don't know which bright spots that person used. Is it from 6 to, 6, or from 7 to 5, or from 4 to, yeah.
Sorry, what are the units? A equals 52?
Millimeters. 52 millimeters.
Okay.
Yeah.
Thank you.
Mm-hmm. So we don't know which actually bright spots were used, right? So we don't know anything about these M's. So direct application of this formula kind of it wouldn't work, right? So, but let me ask you this: what if we can find or use spacing between bright spots and calculate number of these gaps, or use number of these gaps? So we will take delta y, multiply by the number of gaps, and it will be equal to A. Hoping that it will work, will help us. But of course, delta y, it's a, and in the lecture, of course, we calculated actually the formula for delta y, but let's actually do it. Right? So let me calculate delta y. Delta y is a distance between any two adjacent bright spots. And also in the lecture we discussed that all these bright spots are equally spaced. Equally spaced. So delta y equals to, let's take bright spot m plus 1 and subtract the position of the bright spot m. Two adjacent, right? So this is the formula, and we've done it in the lecture. So it's m plus 1 lambda L over D minus, M. M lambda L over D. So M and that M goes. These two terms can be cancelled. Not can be, will cancel each other. And as a result, we're getting that the distance between any two adjacent bright spots doesn't depend on M. It's lambda L over D. And now, so the idea is as I told you. So we need to get number of gaps multiplied by delta y, and it will be A, which that person measured. How many number? What's the number of gaps? Yeah, that's usually the most of the time the answer. That's most of the time the answer. Now let's carefully analyze step by step, right? All right. Most likely, if I were you, probably I would also my answer would be 12. Let's look. So number of gaps. Now let me put the question mark, and let's analyze. So let's assume that we have two bright spots. So we have n equals 2. But how many gaps do we have here? So two bright spots, but how many gaps? Just one. This is delta y, right? So number of gaps is 2 minus 1. Then if we have 3, 1, 2, 3, so we have 3 bright spots. So n equals 3, but number of gaps, delta y, only 2. So 2. Then if you have 3, 1, 2, 3, or 4, so n equals 4, but number of gaps, of course, less by 1. So if you have n bright spots, which you use to measure the distance between 12 bright spots, so n leads to n of number of gaps equals to n minus 1. So we're going to have 11 gaps, right? That's pretty much the trick in this problem. That's where usually students make mistakes, right? So now number of gaps, n minus 1, so it will be 11. So eventually, so yeah, this is the formula which we decided to use, right? And now let me continue this. So here we just analyze this number of gaps, right? So it will be n minus 1 times delta y equals to A. So here we just digressed discussing these n gaps. Okay, so delta y, it's a lambda L over D. Just moving to that side. N minus 1 lambda L over D equals to A. So let's see how many unknowns do we have in this expression. N we know, lambda is given, L is given, D is not known, A given. So we have only one unknown, our goal. So we can find D. So from here, D will be equal to, okay, it just goes here and A goes downstairs. So it will be N minus 1 lambda L over A. That's the algebraic expression. So of course, that person tries to increase the accuracy, right, of the measurements, but of course added complexity to our calculations, right? All right. So if you plug all numbers which are given, yeah. So I will skip, of course, calculations when plugging numbers. So it will be 0.4 millimeters. A very typical number for double slit, 0.5, 0.4, 0.3 millimeters, very typical numbers. So that's the answer. Yeah, in the past I used to discuss this in the recitation class. And yeah, this is the typical place for mistakes, right? So don't feel. All right. Okay, so the last problem about diffraction grating, because so far we solved only one problem. But again, these problems are most of the time nothing but usage of this formula or these two formulas, right? So it's again on the exam most of the time students do reasonably well. Right? especially those who come to classes and know sort of the story. Okay, can I start erasing this? Awesome. Feel like during the virtual classes all the time checking everything to make sure that everything is working. $11. Oh, okay, not, almost like a number of steps in the previous problem. Diffraction grating. Again, I will start with the picture, because once you draw, once you show what you introduce, and then it makes sense immediately to give a number. So, let's say this is my diffraction grating, and that's what I usually draw. So it's a grating. Then, of course, we introduce a screen, right, on which we observe interference pattern. Distance to the screen, I don't remember, 0.5 meters, okay, it's not that much, 0.5 meters. Then, you first eliminate, okay, not first, you eliminate this grating with two lights. First one, wavelengths we know, okay, let me label it as, I don't know, lambda 1. So, lambda 1 equals to 501.5 nanometers. Somewhat orangey or something like that. Then, yeah, and so let me draw immediately. Of course, this red light, okay, first light. Since I use red, I'm going to use also name red. It's going to produce its own set of interference fringes. At the center all the time, the bright spot, all the time, it doesn't matter which wavelengths you use, at the center there will be a bright spot. Then, of course, there will be over here somewhere m equals 1, at the same distance, bright spot corresponding to m equals 1, then m equals 2, and over here will be m equals 2, so let me put m equals 0, 1, this is 2, this is 2. So, complete symmetry relative to the center. And of course, angles, yeah, so this, we can define position of this bright spot using angle. Okay, I will use upper script and subscript because we have m equals 1, we have these bright spots, and also we have first light and the second light. So this is the angle to the first bright spot of the first light. Then, for example, this will be angle theta to the second bright spot of the first light. So the upper script, it's the laser which we use. Then there is a second light, lambda 2, and that's what we need to find. If essentially, we're trying to use this system as a spectrometer, crude spectrometer. So we want to find a wavelength of an unknown light. So it creates its own interference fringes. Right, so this is m equals 0. Then we know that over here, I will write down the distances. So this is m equals 1. Over here, there will be m equals 2. Here, there will be again m equals 1, and so on. Then, so somehow we managed to measure, or we know it's actually given, distance to the first bright spot of the blue light. So it's a y1 of the second light. Again, upper script, it's a light. and the distance is 31.6. Yeah, 31.6 centimeters. And then distance to the first red light, Y11, 21.9. Okay, that's it. So that's what is given, and our goal is to calculate Y2. We need to find not Y2, lambda 2. Yeah, Friday evening. Okay, it's the last problem. So it's a kind of big mess. So where should we start? Okay, I would suggest it's all about these equations, nothing else. So let's just write it down for both of these lights. For light number 1 and light number 2, we'll have 4 equations and start staring at them, hoping that what can be found from this equation, what can be found from that equation, sort of try to see the structure of the solution, right? So that's, I would suggest. So let me write, first I will just rewrite in general for, the diffraction grating for m lambda, and of course then transition to the distances from the angles. And so, since we have information about the first positions of the first bright spots, right? So we just need to write this equation for m equals 1 twice, for the first light and for the second light, right? So, for m equals 1. So for light number 1, so it will be d sine of theta. Careful, so that is the first light, so it's a theta 1. First bright spot. First light, bright spot number 1. So equals to lambda 1. Then the second equation, transition, so it's a y1 of the first light equals to L tangent theta 1 of the first light. So the first 2 equations. Yeah.
So we don't need to put an m next to the lambda?
M, what's the value of M?
Oh, yeah.
Actually, first I wanted to write 1 that in order to, yeah, sometimes students ask, so let me quickly show you. It's 1 times lambda 1. M equals 1. Actually, in my notes I also wrote 1, right, for to make it clearer. So now for the second light. Second light, okay, probably should use blue color. So second light. So it will be D is the same because we're using the same grating. So the same D for both lights. So D sine theta, first bright spot, but on the second light, equals to 1 lambda 2 and the second equation, which allows us to make a transition, y1 of the second light equals to L tangent of theta, first bright spot of the second light. So that is the first set of equations and second set of equations of the blue light. Again, L is the same because system is the same. Both light system is exposed to both lights. So now let's start staring what can be found. So D not known. Okay, let's just skip it. So then theta 1 also not known, lambda 1 is given. Y1 is given, L is given, this is unknowns. Okay, so we have only one unknown in the second equation. So we can find theta 1 from the second equation, plug it in the first equation, And as a result, so we'll have d still unknown. This is what we will find, and this is given. So from the second equation, okay, from the first equation, we will be able to find d. So first here theta 1, then d. Then once we know d, we can move here. D will be found. All right, d will be found. This is not known. Lambda 2 is our global unknown, right? So that's what we need to find eventually. Right, so right now we have this unknown and this unknown, but let's look at the last equation. This is given, this is given. Again, we can find theta 1, 2. From the second equation, we can find this angle, plug it in the first one. This will be given, this will be given. Okay, we found, this we will find, and then we can find lambda 2. So first we need to find theta 1, then find d, then once we know that we can find theta 2 and find lambda. Right? Okay, so let's do it. You know what, let me label them. I feel like it needs to be done. So equation 1, equation 2, then equation 3, and equation 4. So that we will know which equation we're working. So equation number 2. So theta 1 equals to arctangent of, you know, probably I don't want to skip steps. Let me first write the equation and then I will manipulate it. So now, of course, we can solve it for theta 1. It will be inverse tangent of a ratio y11 divided by L. Y is given in centimeters, L in meters, so we need to bring, of course, them to the same units. So it will be tangent of, arctangent of the first one, 0.219 meters divided by 0.5 meters. Okay, let me look at my notes. What's the answer? 23.65. Okay, I will use more 6 weeks. So that's this angle, theta 1, 1. We found this to the first bright spot of the red line. Now, equation number 1. So d sine theta 1, 1 equals to lambda 1. And we need to find d. Yeah, we need to find d. So it's lambda 1 divided by sine of theta, which we just found. First wavelengths of the first slide, it's 501.5 nanometers and divided by 1.25 micrometers. Okay, I wrote in micrometers immediately. Distance between slits in the diffraction grating. Essentially, it's this, right? So, d. It wasn't our final global goal, right? But so for now, we found the distance between slits and the diffraction grating. So we exhausted these first two equations. Now we need to jump to this set. So again, from equation number 4, we should be able to find angle, and then since we know d and we will find theta, we can find lambda 2. So now equation number 4. I think I need to go slightly lower, otherwise I will step on nothing. So equation number 4. y12 equals to L tangent theta 1 with the alpha script 2. We need to find angle. Yeah. So theta 1 alpha script 2 equals to inverse tangent of that ratio y12 divided by L. Okay, and now I'm not going to plug numbers because it's very similar. Now, of course, we'll have to use this 0.316 meters divided by 2. I will just write down the answer immediately. 32.29 degrees. Again, I use more sig figs since it's not the final result. So now the final step. So we need to jump to the equation number 3. Okay, we don't need to do anything. I will write immediately lambda 2 on this side. Lambda 2 equals to d sine of theta 1 of the second light. D we just found. Where is the, yeah, this 1.25. So it's 1.25 micrometers. You know what, since, yeah, it's correct, everything is correct. Let me convert to nanometers. Because wavelengths, I want to get in the nanometers. So this will be 1,250 nanometers. It's the same, I just decided to convert to different units. Okay, with different preferences. So now let me use those nanometers over here. 1,250 nanometers times sine of the angle, which we just found, 32.29 degrees. And of course I will use my notes. 667.8. Can you still see it? I hope so. Can you?
Mm-hmm.
Nanometers. So I'm getting closer to the red light. So 750 is basically red light. So we're getting closer. Dark orange. It's kind of light. So kind of crude spectrometer, right? Using tube lights. But of course, as I said, tons of spectrometers using grating spectrometers. Okay, guys, so that's it. So that's what I was planning for today. It's almost 4 hours, 5 minutes short. And okay, thank you.